I usually start like stupidity. But usually my computer is plug and play with no I think, you can afford yeah, maybe we can try in next 5 seconds just to make sure. Well, from maybe you think it's still not super. You just need to press this button. Yeah. Just trying it real quick. Okay. Typically, it's plug and play for yeah. So perfect. So I'm going to put there. Better. Sure, I have. Yeah, sure. Perfect. Right. I'm exception. Sadece şey yok. Yani şu var olan, şu var falan. Bu kapıyı kapatayım. Girişle kullanırsın.
Hı? Kaç oldu?
Bu kapıyı kapatayım. Girişle çalışmayı yapıyorsunuz.
Onlar girsinler ondan sonra. Gel. Efendim ben. Ya olabilir. Yani şimdi o kafana göre yap. Çünkü ben ilgileniyorum misafirler yani. Şu an yap. Onu olması yerini değiştir. Şimdi arkadaşlar. Ona göre bakarız. Tamam mı? Tamam. Çok da.
Ben şimdi
Arkaya gidin. En üst kata çıkın. En üst kata. Hello everyone. Hello everyone. So it's almost 9. We are good to start. So welcome to our faculty. This is Erkan, one of the conference co-chairs of SPM and SMI 2026. So welcome to our faculty. I have been working here for 12 years since completing my PhD from the University of Tokyo. So I'm very happy to introduce our department and this event. So let me start with introducing our university. Founded in 1773, ITU is one of the oldest technical universities. Right now, we are at ITU Gümüşsuyu campus. It's an historical building. So here, mechanical and textile engineering departments are located. So we have two more city campus, which are nearby. So our main campus are a bit far from here, which only takes about 20 minutes via subway from Taksim Square. So we are right now here, two city campuses nearby, and the main campus is here. So these four campuses are located at the European side of Istanbul, and we have one more campus here at the Asian side as well. To help you navigate in this building, it's rectangular in shape. You will not get lost. If you walk straight and turn at the corners, you will circle back where you started. Okay, don't worry. So who are here? So we have more than 90 guests from all over the world, including Turkey, China, France, the United States, India, the United Kingdom, Hungary, Canada, Singapore, Switzerland, Germany, Italy, Lithuania, the Netherlands, Australia, Japan, Croatia, and Spain. In this conference, we have 12 technical paper sessions, 4 keynotes, and 5 invited talks. We have one keynote each day. Today, Matthew Desprun from Indiana Ecole Polytechnic will speak about computing through the lens of geometry. On the second day, Bernd Pickel from ETH Zurich and Google will talk about designing in the age of AI and spatial computing. On the third day, Tamas Varadi from the Budapest University of Technology and Economics will present constructing and reconstructing surface geometry. And on the fourth day, Brian Weibel from University of Victoria will talk about implicit modeling from dreams, industry, and back. So I'm excited to hear their talks. So we have also 5 great invited talks. So SMI program chairs will give the details of them. And we are going to have one commemorative session in memory of Malcolm Sabin, who unfortunately passed away 3 weeks ago. Now, some quick information about lunch and coffee breaks. If you exit this room and go straight, you will see the lunchroom. Just follow the signs. If you go upstairs from the lunchroom, you'll find the coffee break area. Actually, both rooms have a beautiful Bosporus view. I hope you enjoy it during the breaks. And we have several recess areas. The middle courtyard has an old airplane, so you can go there and take photos. We have the front courtyard with another good Bosporus view here. And finally, we have a very cozy library for our mechanical engineering students. It's even occasionally used as a filming location for TV commercials. So we also have a special treat for you, for the participants, for the second day during the second coffee break. Baklava, probably most of you know it. We order it from one of the best baklava restaurants in Istanbul. For your information, traditional baklava is handmade with 20 or 30 thin layers of dough. So wait for the day two. For our conference dinner, we will have a great experience. We will take a boat and eat dinner between two continents, Asia and Europe. So we will start from the shore nearby and see the old shores of Istanbul during a 4-hour trip. A quick information for the participant who doesn't know Bosporus. It's a channel here. It's a channel that separates Europe and Asia, stretching from the Marmara Sea to the Black Sea. So in this tunnel, we will see both Marmara Sea side and Black Sea side as well. For this dinner, we will meet at 6:10 p.m. at the main entrance tomorrow. So I will give you another announcement tomorrow. So we are at the center of the city. So most landmarks are a short walk or a tram right away. You can see a map in your conference bag. You might also notice a blue ornament hanging on your conference bag. This is an evil eye bead, according to Turkish tradition, looks like this. So it's believed that it protects you from people who envy you. Believe it or not, bring it back to you, your country with you as a memory of Turkey. So here's our organizing team. Actually, I want to thank all of them for making this event possible. As conference co-chairs, thank you to Ergün Akleman, Charlie Wang, and York Peters. For the SPM program co-chairs, thank you to Shuho Kuo, Zuho Kok, and Amir Wangswan. And for SMI, thank you to program co-chairs George Pierre Bonu, Michele Mortara, and Amal Dev Parakkal. So here's our local organizing team. I want to give a huge shout out to my students, Serhat Cham and Alper Taşbekli. They are over there. They probably carried the heaviest workload in organizing this conference. Thank you, Alper and Serhat, again. So now we have a live stream running through the SPM and SMI Istanbul YouTube channel. So here is the QR code for day one. And the recording is being managed by my former PhD student and academic YouTube influencer, Emre Günaydın. He's at the top right now. Thank you, Emre, for recording. Please note that we will obtain formal consent from the speakers prior to recording each session. So these are our sponsors. Thank you very much, our university, Istanbul Technical University. Also, our industrial sponsors, Plasticity and Police Blinds. And Visit Istanbul. Actually, it is an official tourism platform of the Istanbul Metropolitan Municipality. So thank you all coming. Thank you all again for coming. I hope you enjoyed the conference. Thank you very much again. So I want to invite Ergün Akleman for his speech. You want to- Ah,
Ah, maybe I can try this. I generally walk around. Therefore,
ah,
actually, this will be a little bit of emotional speech because the I'm from this uh, campus, not just any campus, this particular campus of Istanbul Technical University. When I was in it's 45 years ago. It's not just 10 years ago, something like that. And then I don't believe, like, I don't even remember when I entered. I can tell you how much time passed. I was in mechanical engineering. I was not initially in computer science. Computer science didn't exist. From mechanical engineering, I moved to electrical engineering. Then they created the computer science. That's how I moved to computer science. It was like I am originated from mechanical engineering in that sense. Therefore, it is also emotional to me. And then not only that, and then I cycled back to mechanical engineering. And then if you look at my recent work, etc., I'm working closely with the mechanical engineering. That's what I will say. Our work, especially shape modeling and then solid modeling, is extremely related to engineering applications. And then we are underselling ourselves in some sense because if you look at our citation rates, etc., overall, engineers do not really uh, understand what is going on. Like if you go and then look at the engineering design conferences, there are thousands of people. And then as soon as we work with the engineers, they become excited. Oh, we want more, we want more, we want more. Something like this. So I think that will be very important. We will have a town hall meeting, SMI and SPM together. Let's discuss a future of our conferences, like what we can do such that we can work closely more. Like I'm not talking about myself. As a community, we can have more closer connections with the engineers. Actually, this is very important because I can come from the mechanical engineering. Hopefully, like we will have the more uh, continuous relationship with mechanical engineering, and then not just the mechanical, because aerospace, material science, they all need us. But not like we solved their FEA problems. We solve their geometry problems. We can collaborate with them to manufacture to do the other jobs also. Does that make sense? We will start with the geometry, and then in the other things we also collaborate. Another important thing is the our paper review process. So we generally go like when we review the papers, we generally say, "Oh, there's no enough engineering." Like, okay, we are not engineers. Like, I'm not saying that I come from this. Like because we are geometers in essence. Like, if we explain the geometry, and engineers took it. That's how it happened to me. They make it better. Makes sense. They make it better because they make it applicable, etc. In some sense, we are theoreticians, like we are close to mathematicians and computer scientists, not the, but this gap is needed to be done, and then we need to really open up uh, so we can just revolutionize because that's in some sense what I'm thinking for the future. We have an advantage because the most of the geometry, higher dimensional geometry, is unexplored. Therefore, you cannot just teach to AI information doesn't exist. We need to develop. Do I make sense? Yeah, that's all I will say. Thanks a lot.
So now I invite Shioku for SPM statistics for submissions.
Um, yeah, thank you, Erkan and all the organizers for bringing this joint conference to this beautiful place of Istanbul. I'm Shahuko from UT Dallas, and I'm gonna introduce the SMPM this year's reviewing and the paper statistics. So There are total of 54 full paper submissions this year. And all the papers go through the two double review rounds. The first round happening on the easy chair, and the second round is actually going on through the CAD editorial manager. And it includes two type of papers. The first type is directly accepted after minor revisions and published in the CAD special issue of this year. And the second category of paper published is actually the promising papers that might go through the major revision process. And it was fast-tracked to the CAD journal and possibly published later. Um, and for each paper, there are three reviewers in each round of review. And each IPC member was assigned 2 to 3 papers in total. So in total, out of these 54 papers, there are 13 papers that are directly accepted to the special issue of SPM this year, making the acceptance rate to be only 24%, pretty low. And we also make 9 papers with major revision to the CAT journal. And out of these 9, 7 papers accepted our invitation to come to the conference to present. It will be arranged in the session 11. We call it the lightning talks. And we also invited some CAT papers published in this past 1 year, including 5 papers invited to present. And there was a recent CAD special issue on the AI plus design, called AI for Design and Manufacturing, and the 3 papers are also invited to present. So out of these 28 papers, we organized them into these 7 sessions. There will be 3 sessions in today, including this CAD special issue session. And there will be 1 session in the second day, 2 sessions in the third day, and 1 session in the last day. Okay. All right. So finally, I would like to thank our IPC members, 64 IPC members coming from all different countries. Without their help, it's really impossible to make this conference program. And again, I would like to thank again and thank all the organizers for making this conference program possible. Okay. All right. Thank you. Thank you very much.
Now I want to invite SMI program co-chairs for SMI submissions information.
So good morning. This is about the SMI statistics. And like, as you know, we have like, three are the co-chairs of SMI papers, technical papers. And we had 74 IPC members. And we had 44 full paper submissions. And as usual, we had 2 double-blind review process. First one through easy chair and then through editorial manager. And we had at least 4 reviews per paper in the first round and at least 3 reviews per paper in the second round. And each IPC member had around 2 to 3 papers to review. And at the end, 18 papers will be presented in the SMI, and we had 15 papers accepted. That is like 34% acceptance rate. And we recommended 7 promising papers to Elsevier CNG through a fast track submission process. And we invited 5 of them to be presented at SMI, and 3 of them accepted. And we have 2 invited papers from CNG. That is totally we have around 20 papers in 5 sessions. And this is like from where all people will be presenting in this conference. And yeah, you know timing, and we have mainly 5 sessions. One is discrete shape modeling, volumes, parametric surface and computational design, neural and implicit representations and skeletons, animation, interaction, and dynamic scene modeling. And we have 4 keynotes jointly with SPM. And then we have an award ceremony of SMI on the second day. Then we have 2 award talks, like Queenie award talks from Brian and Yarek. Then we have 4 Young Investigator Award, like SMI awards on the 4th day. Then on the 4th day, we also have a talk about Malcolm. And then 4th day, we have a Best Paper Award. And it is sponsored by Computers and Graphics. And it has a certificate and total of €1,000. And we have a Best Paper Award committee who will be evaluating all the presentations. And all the papers who has a replicability stamp is eligible for this award. And based on the review scores and the oral presentation, we will make it, or we will decide the best paper. So please make sure to make your presentation impressive, and good luck.
Without something new into it's my pleasure to introduce the main speaker this morning. And today has been very, very influential in at the intersection of large process, differential calculus, for measuring systems, volumes, scalar vector fields, and more usually multiple geometry. All of that is associated with this outputs of the shape and here's the factors. So Paris and also you can use this one. Also, you can this one. We can change. This structure. This is very good. Thank you so much, Jorg, and thank you for no. How do I turn it off? Let me. Okay. Thank you to the organizers of SPM and SMI to invite me. Turkey was one of the few countries that I haven't visited yet, so I'm delighted to be here. And I'm delighted to speak with geometric and simulation type of colleagues so that I can really talk about my research without trying to, be super soft in the way I present things. So I apologize if I go a little bit fast, but because I'm talking to experts, I'm going to go to town. And I promise you all that I will neither use Bézier nor de Casteljon, which I guess I already lost my bet right there, but there will be no mention of these two names in my talks. Okay, so like Jörg said, I will try to explain what I mean by computing through the lens of geometry. So you all know geometry. Obviously, it's been key in many scientific fields. In particular, one could say that I think our ancestors really looked at the world around them and saw that there were some invariants and symmetries in the world. And that's what led to geometry being really the mother tongue of some of the most influential physical theories, all the way to general relativity. Otherwise, I'm not going to talk about GR today, but It's been very influential with lots of great names that are associated with the field, obviously. But obviously, these people, and I cannot hold this against them, they didn't have computers. So they did pretty much everything with pen and paper, right? And so when I started looking into it, now to use this on a computer so that when what we talk about a surface, it's actually either a triangle mesh or point set or etc., but something discrete. All of the notions that were defined by all these fantastic people do not really apply directly, right? And so this is the tension that I've been facing all my life, how to go from the continuum world to more like a finitude, meaning discrete sets of primitives to define a surface. And this is why I've been working a lot on this notion of discrete differential geometry, where really we're thinking about a finite dimensional counterpart to the continuous theory. That's what really it's all about. And we are actually leveraging a lot some of the differential understanding that people have accumulated, and we use this for our discrete computation. So really, I think of geometry as a guiding principle if you want to know how to discretize things. That's what I call the lens of geometry. And in fact, it's been proven many, many times over. I will mention a few examples that if you discretize the geometric principles, you will get predictive power in your computations. Whereas if you try to discretize the PDEs or the results of these principles directly, you're going to have to guess how to discretize things. And most of the time, you will not find a good discretization. So an example of that I like to give, but now it's so dated that I will not explain it. But if you know about the mean curvature flow, you know that you can move a surface so that it's moving basically along the normal. Sorry, I'm still learning how to do this after 25 years of academia. Okay, cannot find the button. So, all right. You want to move along the normal to the surface and proportional to the mean curvature h of the surface. If you can tell me, I would appreciate it. It's on the side. Oh, okay, this one. Thank you. So this normal, maybe you can on a discrete mesh, maybe it's not too hard to compute, but the mean curvature, that's already much harder. And so people have debated how to do this. But again, if you go back to the differential understanding of this curvature, mean curvature flow, you know that it's actually a gradient of the area, basically. It's the direction towards you should move if you want to reduce the area of your mesh as fast as possible. And so in that case, because a triangle mesh is, a bunch of triangles, we know how to compute the gradient, the exact gradient of an area with respect to a vertex. We can actually do this mean curvature flow without even thinking really too much about these discrete entities. Another example was with more in the animation arena. Back in the days when we were trying to do shells, every physics paper were using at least quadratic order basis functions to do simulations of shells. So when we came up with a way to do this on piecewise linear basis functions, people basically thought that we were crazy. That was heresy. That was considered heresy because there was just not enough derivatives to capture shells. Well, long story short, it does work. That's what all these discrete rods and discrete shells are based upon. So at least that proves some people wrong. And there is interest, of course, in academia, but also lots of interesting application that I had the pleasure of doing over the years. But what I really like about discrete differential geometry is that it's very good for educational purposes because it presents really very clear analogs in the discrete world of fairly complex, sometimes continuous notions. So it's easier to explain with a triangle mesh than a smooth manifold. It's always good to make also pretty pictures and fast animation in the context of Hollywood movies or anything. So that's always fun. And also from the computational science point of view, we get to do from time to time some new numerical schemes really based on this lens of geometry. So that has been the three most rewarding experiences that I've had. And today, just to sort of recap a little bit of this, I'm going to show you four vignettes of different types of work.
hopefully they will illustrate all this in four sort of distinct cases. And let's start right away. So the first one is related actually to what Jörg was talking about, this notion of how to do calculus on meshes, because after all, we need to do some kind of computation on meshes. So how do you do this? So I always like to give this example. I usually use this slide in the fall because then sometimes I can celebrate the anniversary. Like last year, I got to almost celebrate its anniversary exactly on the day. But Leibniz wrote this sentence, which basically says it will be useful to use the integral sign to replace omnia. Omnia means for all, like the sum over all the indices, if you want. And that was the first time that really people went from discrete interpretation of formulas where there was sum of infinite small numbers to the notion of integral. And of course, that was very easy to manipulate with pen and paper, paper, pen and paper, that's interesting, pen and paper. And fast forward to now, we have computers. And so now we need to go back to the discrete way of thinking about integrals, right? So there's an interesting back and forth between continuous and discrete, which is right on this discrete differential geometry point of view. So when I started working on how to do calculus on meshes, it was clear to me that by looking at a mesh, at least the notion of differential or geometric quantities were discrete in the sense that they live at very special places. So if you take, for instance, a piecewise linear surface, a bunch of triangles, let's say, then you'll see that each triangle is flat. So there's no notion of curvature inside a triangle, right? It's perfectly flat. But now if you look between two triangles, clearly there's a mean curvature. If you remember that in the continuous world, the two principal curvatures, there's a maximum and a minimum that are supposed to be at right angle from each other. Well, clearly along the edge, you have a zero curvature along the edge, and then a maximum curvature or minimum curvature if it's negative between the two triangles, right? The dihedral angle between the two triangles. So clearly, mean curvature somehow lives just at edges. So you can think of them as sort of distributions, like a Dirac along the edge, right? Same thing, of course, for the Gaussian curvature. If you also know that Gaussian curvature is supposed to be zero for a developable surface, that means that two triangles join with their common edge will have a zero Gaussian curvature because you can always open them to become flat, right? So there is no Gaussian curvature along the edges. But at vertices now, there's clearly something that can happen, which will be if your local one ring is not flat, or not developable, the Gaussian curvature will not be zero. So clearly, there's also a Dirac right there on the vertex. And when you talk about distribution for computational purposes, clearly you need to integrate them, right? So that you can get numbers, just numbers on those edges and nodes, etc. And so that calls for integration. And integration, if you ask a mathematician or a geometer, they will tell you that the tool to proceed with integration is the notion of differential forms, which is really just an anti-symmetric tensor. This is the object that really begs to be integrated. So this is the f of x dx when you see this kind of integral. This is not in the geometric context, but you've seen this type of integral before. The dx really is the one form in this case that you integrate. But very often at the time when I started, it was not used for computation, this notion of forms. And yet we know that integration is naturally good for computation, right? It's even robust to nodes. So it struck me as something that was underutilized and underappreciated. However, I was a little bit stuck because I didn't have the words to create such a mathematical framework. So thank God one of my colleagues, Jerry Martin, pointed me to exterior calculus, which is really a very nice piece of work done by Cartan and people before him to extend the notion of divergence, curl, and grad on non-flat domains. And again, Cartan made this exterior calculus really a calculus based on differential forms, these anti-symmetric tensors that I talked about right before. And so now, as I told you, a k-dimensional form wants to be integrated on a k-dimensional domain. That's why it's this, the k basically indicates the the size or the dimension of the domain. And these differential forms are very nice because, well, they are geometric in the sense that you don't need to be encumbered by coordinate systems. You can actually express them without really a coordinate system. Of course, you can use also a coordinate system, but you don't need it. For instance, when you're dealing with a flux, the notion of flux is a very physical notion, right? You know that if you have a quantity that is a flux, well, then if you have a phase, you know how to compute the flux through the phase fairly easily. And in fact, this exterior calculus is really the basis of all modern differential geometry, including Hodge theory. And it's very nice because it really separates topology from metric, which again, for meshes is nice. It's nice to separate what's topological and what really requires length and dimensions, basically. And it turns out that it's only based out of 7 basic operators. So that seems like a feasible thing to discretize. So we did this. That's called discrete exterior calculus. Basically, like I said, we use the mesh as a computational structure. So we store the, so we see, first of all, the simplices of a triangle mesh, let's say. It has been extended to non-simplicial meshes, but let me stick to simplicial meshes. So we see all of the simplices as basically entities, and we can create chains. Chains will be just linear combinations of those simplices. And then from this domain, if you want, the chains represent sort of a domain, we can store now k-dimensional forms by just integrating a continuous form on those simplices, because the mesh, if you want, is a bunch of very well-defined small domains. So now we can integrate, for instance, a 2 form on a triangle. We can integrate a 0 form on a vertex, etc. So we call sometimes these discrete forms cochains because they are the dual, if you want, of the chains. And so now complicated notions like the D, which is the exterior derivative in exterior calculus, can be actually done quite easily by basically using Stokes. If you have heard about Stokes' theorem, this is basically saying that the integral of the differential of a form omega over a domain is nothing but the integral of omega itself over the boundary of the domain. This is called sometimes, divergence theorem. I mean, there's plenty of names. Stokes is the general phrasing of all this theorem. So it turns out that here you can see that the D basically is equivalent through adjointness to a boundary operator. The boundary of a simplex, we know how to compute this. So guess what? That means that you immediately know how to compute D because you have a well-defined boundary on your meshes. And by the way, because of this definition, D is purely topological. You don't need to know the size of a triangle sigma, for instance, to perform this Stokes theorem. So this is what I was talking about, separating topology from metric. And that leads to plenty of things like homology, cohomology. I'm not going to go through the details, but once you have this kind of notion, then all the continuous notions go through, basically. And same thing for the Hodge star. The Hodge star is also a very interesting operator for exterior calculus. And here, if you don't mind having a low order Hodge star, there's a very nice duality between the primal and dual of a mesh that can be used to compute a low accurate but extremely versatile Hodge star on meshes too. And then from this, you can assemble what we call the Durham complex. So it's, if you're not aware of it, it's a little bit complicated, but basically this is the discrete version of this. So you store scalar values on either nodes or tets. Let's say this is for 3D. So nodes or tets are used to store scalar values. Really, this is more like a density value instead of scalar value, but basically it's the same thing. And then you can take gradients of a function on nodes that will give you a function on edges, values on edges, and you can take the curl of the edges to give you a value on faces, etc. So all of this satisfied the normal exterior calculus point of view, but now completely discretized on a simplicial mesh. That's why it's nice. And it turns out to be basically just a simple exercise in matrix assembly when you understand it properly. So that means, for instance, you can do Hodge theory directly on triangle meshes. All the notion of harmonic forms, cohomology, all of this carries through intact. You can even do finite element by using Whitney basis function, not just associated with nodes, but also associated with edges, like finite elements associated with edges and facets and etc. So that's quite powerful. And you can even, if you're not happy with the piecewise linear accuracy, meaning first order accuracy, you can go to higher order accuracy using subdivision or even spectral basis. So I'm not going to bore you with the details, but with this, you can do lots of application all the way from Hodge decomposition in all of its glory, 5-term components, decomposition, sorry. You can do plenty of geometry processing all the way from parametrization to geodesics to even masonry. And you can even do animation. So we use actually this deck point of view to basically make sure that vorticity is really advected in a domain, in the 3D domain to simulate Navier-Stokes properly. Okay, so this is the most abstract part of my talk. Now let me go to something much more practical. Although underneath it all, there is still the same level of, we're trying to make sure that what we do exactly mirror the continuous world, right? This is the good thing about discrete differential geometry. We really try to mirror the continuous world. In effect, we're not inventing anything. We're just explaining how to adapt this continuous thing to the discrete world. So the second part is about grooming. So grooming, if you don't know about it, it's how to grow feathers or hair on digital characters. So for instance, if you take Remy, the little rat from Ratatouille, you can imagine that no animator or no artist that is still alive, at least, has taken time to enter all the hair by hand, right? This is not possible. So how do you do this? You basically define a vector field on the surface of the rat, and then you will grow the hair along the vector field. So that asks the question, how do you design a vector field on a non-smooth surface? So that leads us to this notion of vector field processing. And of course, when I say vector field, could be actually direction field. Sometimes the magnitude does not matter. For instance, for hair, magnitude is not really important. It's the direction towards which you want to grow the hair that matters. It can be also frame field. I'm not going to talk about all this. I'm just going to stick to direction field today because that's simpler to explain. And we wanted to provide notions for artists to be able to design some kind of a vector field like this, where they can control where the maelstroms, where the singularities, if you want, of the vector field appear, right? Because if you think about hair, either the hair of on somebody's head or for the rat, clearly there are spots within the vector field that are more salient, more visually striking than others. For instance, a bald spot where the vector field goes to zero, basically, or where there's a singularity, if you want, will be very visible. And the artists really want to put these singularities at particular places, sometimes hidden places, or sometimes very visual, very obvious places, so that it looks in a very particular way. So we wanted the artist to have control over both the smoothness of the vector field, but also the placement of the singularities. And to do this, there were plenty of methods because we have a very healthy geometry processing community. So there was lots of great ideas, but we actually decided to use another tool, which was connections. Connections, if you want, is one step further from exterior calculus in the sense that now you're trying to talk about parallel transport of vector field on surfaces. So this is what a connection one form is about, is basically how do you define the notion of parallel transport on a triangle mesh. So it turns out that it's actually not that hard. And again, we're going to rely on this very simple pair of triangle idea. And between a pair of triangles, you can think of the edge in between as a hinge, right? Like the hinge of a door. And here is how we proceed with parallel transport. It's very easy. Imagine first that you store a vector, a blue vector here in one of the two triangles. This vector, somebody give it to you. And you're being tasked to actually parallel transport this vector to the other triangle over. So parallel transport, when you're in the plane, parallel transport is trivial. It's just translation. But on a non-smooth surface, lots of geometers thought about what is the right way to think about parallel transport. But here for triangles, there's a very simple way. I told you, actually, I alluded to it a little bit earlier. When you have two triangles, you can always flatten the hinge between the two triangles without deforming the triangles, to make them flat, to make them live in the same plane. Once you do this, you are in the same plane. So you can just translate the blue vector to the other triangle, no problem. It's a plane, it's just a translation. And then you fold it back. That's all you have to do, right? So conceptually, parallel transport, at least this notion that I just explained, is really trivial. Now, of course, this is a conceptual idea. It doesn't tell you how to code this up, okay? And most of you are interested in how to code this kind of things up, so let me explain. Basically, for every edge between two triangles, let's say triangle I and J, you're going to store just one angle that explains the change of basis between triangle I and triangle J. So how does it work? Basically, you start from all the triangles of your mesh, you assign a coordinate system, two-dimensional coordinate system inside each triangle. You can pick whatever you want. Typically, people will pick coordinate systems that are aligned with one of the edges. But again, you can do whatever you want, just random assignment of coordinate frames on each triangle. You just need to remember what you did when you define them. And then the number that I alluded to, the angle between the two edges, is simply the smallest angle that you need to rotate one frame from I to the frame in J. Okay? This angle basically tells you what type of rotation do you need to go from the frame in I to the frame in J. And of course, I lives in its own tangent plane, meaning the first triangle, and J lives in its own tangent plane, meaning the triangle J. But the rotation is to tell you how the two frames are related. Again, thought of as living in the same plane because you flatten the hinge map in the plane. Okay, so that means that, basically, why is this an implementation of this? Because now, if you know the two coordinates A and B, or X and Y, sorry, or U and V, I guess, U and V coordinate of this guy in this frame, you will know exactly the coordinate U and V of the parallel transported vector in that frame by just hitting the UV coordinates by the rotation by the small angle alpha. That's it. So this gives you a concrete numerical way to perform this conceptual parallel transport. And it turns out that it's not hard to see or to prove that this notion of parallel transport is nothing but the Levi-Civita metric connection one form. So basically, it's a very natural connection that, guess what, geometers have found way before we started thinking about triangle meshes. And in fact, all the notions of Levi-Civita already show up even on triangle meshes. For instance, if you have a non-flat one ring and you start with one triangle, you parallel transport it around the vertex in a loop, if you want, around the vertex, you will see that you will not come back to the same vector. And that's called holonomy. It's basically the mismatch that you have when you do a little loop, a parallel transport around a little loop. If locally you're not flat, you're going to not get the same angle. And again, geometer proved that this difference of angle is nothing but the integral of the Gaussian curvature if you use the Levi-Civita connection. The integral of the Gaussian curvature over this region that is bounded by the little curve. So by the way, that means that you now know the the discrete Gaussian curvature for a triangle mesh is nothing but this angle, which turns out to be 2 pi minus the sum of the tip angles. It's not a very difficult derivation. Okay, so we have defined a notion of Levi-Civita connection. Turns out that Levi-Civita is just one particular type of connection, but you can actually extend it to any principal connection. What you simply do is, instead of doing this very naive or very canonical way of doing parallel transport, instead of just doing one single translation here from this vector to this vector, you add also a tiny adjustment, a tiny rotation. Okay, so this is not the same angle as this guy. This angle was to really define the Levi-Civita. Here I'm just saying from the Levi-Civita, if you add another adjustment rotation between two triangles, you're changing the notion of connection. And again, this is something that people know very well in the continuous world, because Levi-Civita, again, is just one particular case of connection one form, but you can come up with as many as you want. And so going back to the problem of designing vector fields such that you control exactly where the singularities are, etc., we had the idea now that, hey, now that we have this notion of parallel transport, could we compute these little adjustment rotations that I just defined between two adjacent triangles who have a little degree of freedom, this adjustment rotation? Could we make them such that the holonomy that we had initially, remember the Levi-Civita connection? When you were doing a little parallel transport around the vertex, you were not getting back to the same triangle. What about we mess up with the Levi-Civita with this extra rotation, adjustment rotation, such that now on all the little loop, the holonomy is 0, meaning that you're guaranteed that when you do parallel transport, you come back to the exact same place. Well, it turns out that you can actually do this if you count the number of unknowns, because we have this little adjustment angle that you have on every pair of triangles. If you look at this counting compared to the number of little loops that you can do on a mesh, you realize that there's more little adjustment than number of loops. So you can always kill the holonomy almost everywhere. And I say almost everywhere because math is still there to annoy you. There is, again, in the continuous world, something that is well known as the Poincaré-Hopf theorem that tells you basically that somehow the curvature that you kill by changing the holonomy to 0 has to go somewhere. You cannot kill it everywhere because that would mean that your surface is suddenly magically flat. It was not flat, it was a curved surface. So you have at least one singularity that has to be somewhere, or multiple ones if you prefer. Again, you let this handled by the animator where he wants or where she wants the singularities. And once you know this, I told you that there's always plenty of adjustment angles that you can pick. What we recommended in one of our papers was to find the smallest adjustment vector, meaning the L2 minimum of all the possible adjustment angles. I don't know why I put vectors, it's angles here. So that you don't deviate too much from the Levi-Civita connection while killing the holonomy almost everywhere except at singularities. And so what this creates, yeah, by the way, recently we realized that this notion of smallest actually meant that we were minimizing the torsion. So at the time, we didn't know that it was actually torsion of the connection. So if you want to understand why it is, go back to a SIGGRAPH paper from last year, but this is relevant to my discussion here. So now that you have these adjustment angles that are particularly picked so that they kill the holonomy of the Levi-Civita, that means that now you can start from one vector in one triangle of your mesh anywhere, and you can parallel transport it in any direction that you want, in any order that you want, because you will get a completely smooth vector field. Because there will be no disagreement whether you turn left or you turn right, you will get back to the same value. So you can do really a propagation over the whole mesh, and you'll get a vector field, a direction field on your mesh. And because it's super close to the Levi-Civita, because you pick the smallest adjustment, it will be very smooth. And because it's exactly kills the holonomy everywhere except at the singularities, it guarantees that the singularities that you picked, the vertices that you picked to be the singularities, that's where your vector field will have a singularity and nowhere else. So that means that, for instance, for this bunny, if the artist picks those places for the singularities, whatever reason, they will get with just one single linear system of a very sparse matrix, so it's super fast. You will get what we call a trivial connection because it's a connection with almost zero curvature everywhere. That defines a vector field the way the artist wanted with exactly the right placement of singularities. And of course, there was no singularity in the back, and you see that the solution has no singularity indeed. So it really respects exactly the singularity. And it turns out also that this is very robust to the meshing quality. So if you have very nice and fine triangles here, it gives one result. If you have messy triangles with very badly shaped triangles here, or a refined set of triangles here, for instance, it still gives you visually the same vector field, basically. And so now if you give this to animators, and we gave this to Pixar animators, well, they have fun with this. So for instance, this character is entirely done, even the feathers is done with this method. And so when you work with Pixar, that's good, you get little trailers. So to present our paper, they gave us this little trailer using our technique. Okay. So this grooming project was nice, but then we said, okay, we've been grooming horses. Can we groom also data? Meaning, can we use it for other applications, not in 3D, because 3D can be boring? Can we go to higher dimension? And it turns out that, to my surprise, it did work almost exactly like grooming, but now for data science. So let me explain the problem that we found that's required the same type of math to solve it. It's called dimensionality reduction. I'm sure you've heard about it. You know that if you have a data set where every point of your data set lives in a super high dimensional space, let's say R to the power big T, where T is really large, and you want somehow to project it to a small dimension, right? Let's say a Euclidean space of dimension little t now, where little t is much smaller than big T. So basically, you want to try to find a Euclidean embedding of your high dimensional space now into low dimension. And of course, there's plenty of this. You can just pick random assignments, but that's not good. You want, in a way, to make this in the most isometric way possible, meaning that the distances that was in R to the power big T should be proportional to the distances that you have in R to the power little t, meaning that the points should be relative to each other, still the same way they were. So you try to do a projection for high dimension to low dimension, where the vicinity notion between points stays the same. Here's an example for a particularly large big D, which is 3, and a particularly small little d, which is 2. Okay, just to get the idea more obvious. So if you see this little piece of rolled cheese, or whatever you want to call it, a little ribbon, you want to unfold it into 2D without changing the distances between pairwise of points inside the ribbon, right? So you really do an unfolding like this. And it turns out that people call this nonlinear dimensionality reduction, because of course you know of other ways of doing dimensionality reduction. You know, PCA, for instance, right? Principal component analysis is a way to do dimensionality reduction. But if you apply it to this guy, it will just project the ribbon flat, which is not what you want. Here you want to uncurl it, unfurl it, and unfold it flat. That's why it's a nonlinear dimensionality reduction. And it turns out that people have done this already, all based in eigenanalysis. There's plenty of methods. There's a method that's called isomap that takes the pair of all the geodesic distances between your data set, your data points, and then from this big matrix of all the distances between every pair of points, they find an embedding in a low dimension. And this one is most probably the one that is used the most, because it's very robust to noise, because you really take into account every distances, basically every pair of distances. And then there have been methods that are much more economical, in the sense that they only look at your direct neighbors. The problem is, and there's a huge amount of them, from Laplacian embeddings to locally linear embedding, etc. The problem is that they become very brittle. So this method works great if you have data that has no noise. As soon as you add a little bit of noise, it just collapses. So that's why in practice, people prefer isomap. And it's been really hailed as a great extension of PCA, because it does basically nonlinear dimensionality reduction for just basically a big eigen analysis of this distance matrix of the geodesic distances. So how does it do it? Without getting into the details, like I said, you want all the geodesic distance between your point in high dimension. So what do? Basically, from all your points, you create some kind of a graph of nearest neighbors. So for every point, you link it to its k nearest neighbors, where k is small. That creates a whole graph of your data. Then on this graph, you run Dijkstra's algorithm to compute all the pairwise distances. That will be your approximation of the geodesic distances. So basically, you perform a Dijkstra approximation of the geodesic distances on this k-nearest graph, k-nearest neighbor graph. And then from this matrix of all the distances, there's a very nice mathematical tool that I will not discuss, but a very simple, it's called multi-dimensional scaling, a very simple eigenanalysis of this matrix that tells you exactly how to map it after that into low dimension, so that the isometry is as good as possible. So this part is exact. In a way, it's the optimal way mathematically to do it for a particular notion of isometry. But this part is actually really bad. The Dijkstra algorithm, I never really realized until we got into this project how bad it could be. And here is why I'm saying it's bad. And I hope that your geometer brain will react as strongly as I did when I first saw this. So if you take even points that lie in a 2D plane in 3D, and you ask for this isomap to project it into 2D, you would expect that the projections should be perfect, right? I mean, it's a flat bunch of points. Actually, it's not. So that means that in this particular case, where PCA will give you obviously exactly the right answer, isomap is much worse. They get like up to 5% of inaccuracies, whereas PCA is exact. So that was the first sort of surprise. And why, by the way? Because Dijkstra, of course, it uses the graph as a way to estimate distances. So as the graph never goes straight, you overestimate, in a sense, all the distances. And so when you ask to project after that, obviously there's going to be errors. Then if you give a bunch of points that are on a developable surface, I would say as a geometer, I would hope that they do a pretty good job. And again, it can go widely wrong if you use this isomap. And finally, if you have even a hole in your data, like this big hole in this ribbon, then the hole gets completely magnified. Again, why? Because in the Dijkstra algorithm, to compute the distance between this point and this point, it has to go around the hole. And so the distance is in a way messed up by the presence of the hole. Then if you think about it, this is a big hole, obviously, but between any 2 points, there's a hole too. We're talking about samples. So there's holes everywhere. That's why even for the flat case, you always will have errors. And so we decided that because Dijkstra is the root of all evil in isomap, why don't we try to change it? And it turns out by using exactly the same ideas as the trivial connection example for grooming that I told you about, we can actually fix it. So I'm not going to go through the details, but basically we start the same way. We start with k-nearest neighbors, but now from the k-nearest neighbors, we estimate a tangent plane, a little bit like the triangle before. So we have, for every point, we have a plane, just like the triangle before. And then now for two neighboring planes, we compute the equivalent of the matrix, I mean, the angle that was the angle of the Levi-Civita connection, how to move from one coordinate frame to the next. So here we do the same thing. For every plane, we assign a random coordinate system. And then we find the matrix that will bring you one coordinate system to the neighboring coordinate system. This is exactly a connection too, but now in high dimension. But otherwise, exactly like it before, and it turns out that there is a closed form solution from this through a simple SVD, so no complication. And then we can actually evaluate the geodesic distances much more accurately than Dijkstra using something called Cartan's development. Not going to go through the details, but basically what it does the parallel transport of the curve of the path between 2 points. So if you think about one point I going to this point IM, I1 to IM, if you do the parallel transport of the curve into the tangent plane at I1, you see a curve like this. And now if I'm asking you what is the distance between I1 and IM, Dijkstra will just sum all these little distances here. But with this Cartan development, you actually know that a much better estimate of the distance is simply from this point to this point. Why? Because in Cartan's development, this parallel transport idea of curves, it turns out that a geodesic is actually a straight line. So if you want the geodesic distance between this guy and this guy, just take a straight line in between. So by doing this, you remove all the zigzagging that Dijkstra does or the going around a hole to get to the other guy. Here you can cut through and avoid the inaccuracy of your geodesic distances. And so by changing now 6 lines basically on the isomap code, you can now, for instance, get the hole inside this S to be the normal hole. And unlike the original example, it turns out, okay, I'm showing you 3D examples of like 4, how to call this? petals of a rose kind of thing that should project into petals, but when you use isomap, it's completely degenerate, whereas ours keep the shape of these petals. And you can even try it with real images. I told you that you can consider these points in high dimensional space to be, for instance, images. So this is a 64 by 64 or maybe 128 by 128 picture of an A. And you see that the A has different scales and different rotations. And again, by sending randomly the images of the A to isomap, isomap can sort them out based on scaling and rotation. So it's very nice. It turns out that our method does something very similar in this case, so it's hard to argue that we're better than isomap. But what we did after that, we took the isomap results, we removed a bunch of the images that were all this point here, all these red points in this region. For us, no problem. We just find basically the same embedding with just the missing images missing. Whereas isomap get completely confused, right? Because now Dijkstra will have to go through the hole and you mess up entirely all the dimension. So that shows you how much more stable you are with this. Okay. So for my third vignette, I go to something very different. Again, the SPM crowd, we enjoy it to have a little bit mechanics or simulation in all this. So it turns out that I didn't know personally. I learned a lot from my different colleagues, in particular Jerry Marsden, that mechanics is actually geometry. I'm not going to try to explain this in all the gory details, but maybe it's worth still going through this Hamilton stationary action principle. I don't know how many people are aware of this, so I'm just going to explain with the hands. So don't expect that I'm being very mathematically correct, but I'm trying to get the notions across. So if you think about a mechanical system of any kind, you can think about what we call the configuration manifold, meaning all the positions, all the configurations that it can take. So then when you have your mechanical system, let's say this weird bunch of cubes with some smoke being blown at it, it starts at one point on the manifold, let's say at times t equals 0, and you know that you want to reach this location at times t equal big T. And the big question is, how does the system move? We know that it's moving on the manifold because it has to follow, has to be a configuration of your system, but you don't know which path. And Hamilton's was one of the first ones to say the right path is special in a geometric way. And this geometric way is simply that it's extremizing a score, if you want, which is the integral along this path of what is known as the Lagrangian. And the integral of the Lagrangian is called the action. That's why this is Hamilton's action principle. And so the physical path is one that will be a critical point of the action, meaning the integral of this Lagrangian. In mathematics, people write it like this. So this is a variation. You see the variation of this with 0 and t being fixed, because that's the extremities of your path, will have to be 0 so that the path is a critical point. So if you think about it naively, you could say, well, if I do the derivation, I found that the optimal way to get this action to be extremized is nothing but F equal ma. So what's the big deal? I was using before my Newtonian point of view. Why would I go to the Hamiltonian point of view? Well, it's very different in the sense that Hamilton thinks about physics in a boundary value problem, meaning that you really know the first point, you know the final point, and you give a description of the path in between. Whereas the Newtonian point of view was more of an initial value problem, meaning you know your configuration Q here, you know Q dot, meaning how the configuration was going towards, and then from this you guess where to go next. So you go one step at a time with no sort of memory of all the path before. Whereas the Hamilton's stationary action principle really says the whole path is optimal. So what's useful for this when you do numerics? Here's the idea. We can actually exactly use this geometric principle to create a time integrator. Let me explain how. First, we discretize things. So you know you're good at this. So instead of a continuous path on the configuration manifold, you look at a discrete path of the configuration manifold, right? So you discretize typically the time, right? So time stepping of your simulation. No problem there. So you start at Q0, then Q1, Q2, Q3, Q4, Q5. And then you ask, how do I turn this integral into something that I can actually compute from those samples? Well, guess what? You do quadrature, right? So for instance, you say the integral between two consecutive points qk and qk plus 1. This is the integral of the Lagrangian. I'm going to define it to be something. For instance, midpoint quadrature, right? That's one way to do quadrature of the integral thing. So you have now a discrete notion of action between two points. And then what you're going to do simply is you turn the integral into a sum. You're doing a reverse Leibniz, basically. So the integral turns into the sum of all these little actions. And now you realize something very simple and nice. If this point is qk, when I move qk on the configuration manifold, the whole path does not really change. The only thing that changes is the path between qk and qk minus 1 and qk and qk plus 1. That's the only two things that change, right? If you move just qk. And so that means that from qk and qk minus 1 and qk plus 1, you can say, okay, now let me fix qk minus 1, let me fix qk plus 1, and then I want to know what is the condition on qk so that the whole path between qk minus 1, qk plus 1 is optimal. And when you do this, you just do a derivation of this. You find a simple equation that you have to solve, which basically links these three terms. Once you have that, you're done. Because now, in a weird twist of the way you think about it, here I was thinking to derive it, I was thinking that qk minus 1 and qk plus 1 were fixed, and qk was the varying one. I got an equation. But now this equation, it's basically a discrete Euler-Lagrange equation, if you want, of Hamilton's principle. Now this equation, I'm going to use it in reverse, meaning I'm going to suppose that qk minus 1 and qk is known, and I'm going to solve that equation to find qk plus 1. So I assume that qk plus 1 was known to get the equation on qk, but then this equation on qk is telling me what to solve to get qk plus 1 instead. And this, amazingly enough, has great properties. It can be shown to be symplectic, which means that basically the energy is very well preserved. There's plenty of symmetries, like for instance, the momenta is preserved and everything. So there's lots of properties that can be derived from this. And it turns out that we had fun with this. We did a lot of Lie group integrators and integrators for cars, for helicopters. We even did molecular dynamics. Of course, it takes a little bit more time for molecular dynamics. But all of this with this idea of variational integrators that really follow the geometry of mechanics. So that was my point of view, is that even in mechanics, you can think of mechanics in a very geometric way. And more recently, over the last 5 or 6 years, because again of geometry, I got fascinated by this other methods that was studied by Boltzmann, that basically, and I'm not going to talk about this today, but he thought about the configuration manifold in a very different way. But again, it's the geometry of the manifold that he considers differently. And the beautiful thing is that it creates a method that is neither the traditional macroscopic way where you solve for Navier-Stokes pressure, blah, 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 nor the molecular dynamics, which would be way too slow to compute for fluids, but it has something in between that is called mesoscopic. I'm pointing you to a class that will, a course that we'll teach at SIGGRAPH this summer. If you want to know, you don't need to come to the course. The course notes will be online, so feel free to look at the courses. But the course notes. But the advantage is now for fluids, we can really do a lot of fun simulations, both for computer graphics and engineering. So we can do, for instance, surface tension problems like this paper boat on water. We can do stone skipping, where you can throw a stone and see it skip in water or not. So when my students does it, it does this. When I do it, it does this. It shows you my skills, but it's fun to see that it's exactly doing the right thing. We can even like put water in a container and drop some more water. We see all the bubbles being formed and everything. And all of this in just a few seconds per frame. So compared to back in the days where it would take literally hours per frame, we came a long way. We can also do more on the engineering side. We can do virtual wind tunnels. So we were able to use some known examples of car designs, and just run them through our own LBM-based, Lattice-Boltzmann method-based wind tunnel and get the result within 3%, like the industry wants, basically. So that's nice to see that even for engineering application, that works very nicely. And then this year at SIGGRAPH, we'll show how to mix sand with water. So here you have water dropping on top of sands, and then eventually the sand sort of separates from the bottom and just goes back to the surface to float, which was nice to have this sort of behavior captured in applications. Okay, so for the final vignette, that's going to be very fast, I wanted to show also how learning can be both interesting and annoying. I still like learning. There's plenty of things that I find annoying in the learning community, but I still like it. And so here's my take on learning based on the focus that I've had over the last 3 years. I was trying to say, how can we mesh a sign distance field? You all know about sign distance field. That's basically implicit function, but a particular one, which is just the sign distance to the surface. So let's say I give you a sign distance field, and I want a mesh of the surface that it represents. Okay, so as geometry processing people, you know that we can use marching cubes or dual contouring, solve problem, right? But then you start to think, well, marching cube and dual contouring is typically using piecewise linear interpolation between the values at the nodes, and that has to be not optimal. So basically, the mesh that you get out of marching cube, there's no way that's the optimal thing that you can get. And the idea is, hey, what about if I use data to sort of learn something better than a piecewise linear interpolation so that I can get a better mesh? And this fits in the whole 3D shape learning technology that people have been using thus far. So you can start from SDF or from a photo or anything, and then have a neural network, have a learnable 3D representation that sort of is optimized on your network, and then eventually return a shape, right? So here I'm going to talk only about the SDF case, but it could have been other types of input. And of course, you're going to train it on plenty of examples. Let's say, for instance, CAD shapes, if that's what you have available. And you can, after that, validate it on other shapes that have nothing to do with CAD shapes, so that nobody can argue that it's just learned overfit on your data, right? And so that's what we did. And we came up with so first of all, it turns out that there's plenty of learnable representations that exist. I created like 2, 4, 6, a family of 6 different representations that was valid 6 months ago. I'm sure by now there's 8, but that's the way it is. The problem is that if you compare to the baseline, which is the marching cubes, it has been improved into a neural marching cube, and dual contouring has been improved in the neural contouring. But for these 2 examples, 50% of the results are either not watertight or not manifold, sometimes either. So as a geometry processing person, that hurts. I don't like this kind of lack of guarantees. And it turns out that the other extensions to marching cube type of methods don't fare much better. All these orange labels is where you cannot say, meaning sometimes you're lucky, it's good, sometimes you're not lucky, it's not good. So this is annoying that you cannot guarantee lots of very basic notions for mesh extraction. And so what we did, I'm a little bit late, so I'm going to go very fast. What we did is to use, create a loss that we call the Voronoi loss, because it's basically used to create a Voronoi diagram. And we basically try to create a representation, a learnable model, where we have Voronoi sites inside and outside the shape, and we optimize the positions of these Voronoi sites so that the shape is best captured. So you start here on a regular grid, the nodes are on a regular grid, and then you make them move with this Voronoi loss, you optimize it so that it captures the shape. And once this technology is in place, what you can do is start learning from lots of sites how to directly go from the nodes on a regular grid close to your surface to where this Voronoi sites should go so that your shape is best approximated. So you learn this process instead of doing the minimization all the time for any new shape. You try to learn in one step how to get the Voronoi sites at the right locations. And so that's basically 2 neural networks, one to guess the position of the Voronoi sites, and one that guessed the occupancy, meaning which Voronoi sites are inside, which one are outside. This one is the smallest network because you only have to guess plus or minus, basically. But then after that, once you learn on a bunch of meshes, then you can use it on any mesh and directly get, by extracting a subset of the Voronoi facets, you can extract a watertight and manifold representation of your mesh. And it turns out that on SDF that we tried, even complicated ones, we train it on CAD and we, after that, evaluate it on non-CAD meshes. Of course, if it's fine enough, you really cannot tell much of the differences, but when it's very coarse, clearly the Voro mesh is actually much better and, of course, guaranteed to be watertight, etc. And then we did another version that's called Pong. I'm going to escape it, but it is basically the primal version. So instead of using Voronoi, we use more like Delaunay. And we mix it also with quadric matrices. And now it beats even Vomesh. So it does an even better job as Vomesh. So this is the state of the art as of 6 months ago. Compared to the ground truth, you see on this very coarse data, we get something decent. It's not perfect, of course, because it's super coarse data set, super coarse SDF, but it's much better than the other cases. And we show that it is on all the metrics, it is better. But then we thought to ourselves, okay, we have to come up with all this primal dual Voronoi cells, Voronoi sites, etc. It seems a little bit complicated. It was great because we were using computational geometry to do machine learning. So I loved it. But then at some point we said to ourselves, wait, the whole point was to try to say polynomial interpolation, like piecewise linear interpolation, is a little bit sad to be used on signed distance function. It's better to learn how to better interpolate. But why do we have to go through this learnable representation? In fact, what we can do is simply upres, meaning super resolve, if you want, the SDF. So if you have an SDF that is 32 by 32 by 32, well, then bring it in a machine learning way to 128 by 128 by 128. Then on this finer SDF, extract it with marching cube, and then you're fine. You get a much better result. And that's actually the case. We will show a paper this year at SIGGRAPH that shows that, for instance, for a marching cube on a coarse grid data set, you get something where all the small tentacles are completely lost here. But if you use our super resolution SDF and then a marching cube on it, of course, you get something very close to the ground truth. For at least for not only better results of all the other methods that I showed you, but actually even faster. So by bypassing completely the notion of learnable model, you actually get faster. So to me, that's an example where, okay, learning is great because it offers another way to think about the problem by learning from data. But sometimes we get into ways of doing things by habit, and then we discover that there's way simpler ways to go. So this is also what's interesting about learning. I think there's a lot of things to be changed to improve upon it. The good thing about this upresing is that we can do it also on animation. So if you have a low-res animation with very few frames, you can actually upres both in space and in time to get a simulation that is much more complex, obviously, because you upres both the spatial resolution of your grid and also the temporal resolution of your simulation. And by the way, this simulation was upresed from the left simulation, but trained on just a ball flow, a flow around the ball. So that's really generality right there. It generalizes from this to this pretty easily with machine learning if you do it right. So this wraps up my talk. I wanted to show to you that computing through the lens of geometry can be quite useful, not only in low dimensions, but also in high dimensions. So I like to call this sometimes geometry-powered numerics. And what I really like is that it's blurring the line between discrete and differential treatments. So in fact, it's quite interesting sometimes to talk to mathematicians about, for instance, exterior calculus, etc. And they understand exactly what we're doing because, well, we're using the differential meaning just applied or at least adapted to the discrete setting in a sometimes straightforward, sometimes a little bit more complex way. And we are able to deal with nonlinearity in a interesting way, like for instance, connection or very nonlinear things, right? If at school you learn about what's the name of uh, these connections? Anyway, uh, connections can be written by pen and paper in a very complex manner with lots of derivatives, etc. Of course, in the discrete world, we are able to do things that are much simpler, which doesn't mean that it's simple, but it's at least simpler. And of course, that will require, if you really want to enjoy the generality of geometry, that will require that you learn a lot of things about physics and exterior calculus, etc. And for the young people out there, you should learn about this either by going to class or ask an LLM now. Maybe it's just as fast. I don't know. I'm not young, so you'll have to decide. But you're at the age where you can learn all these things, so don't miss the boat because otherwise it becomes increasingly hard. And obviously, machine learning, I believe there's also much more to do on this topic. And on this, I wanted to thank all the people that I worked with. It's a wonderful thing to be old because you get to know a lot of former students, and some of them, for some reason, still want to work with you. So that's quite wonderful. So I want to acknowledge that most of the work that I've been talking about was actually done by other people. I just claimed that it's. Thank you so much.
Students or questions that is most questions can be asked. So I'll just send you my microphone. And it's not just really good. We can that.
I just have a question that Laura mentioned that HDF will be your high. How accurate geometrically and what is the guarantee that you have the correct number of one pieces when you look at the mesh that exactly
So I'm sorry, I hear the sound really poorly from here. So I understood the question, but which part of the talk were you talking about? Oh, the formal mesh. Okay, the machine learning way. So what do you mean by accuracy? I mean, what people do is they look at the chamfer distance. So basically some weak form of Hausdorff distance between the reconstructed mesh and the ground truth mesh. So you start from a ground truth mesh, you compute on a regular grid of a given size the signed distance field. Then you give this to your machine learning algorithm, it outputs a mesh, and then you compare the output mesh to the ground truth.
Okay, sometimes people um, exact
Right.
how we can correlate between the
So again, it's chamfer distance. I don't know if you're aware of it. It's basically samples and distances between the samples. So because it's differentiable, so people have used this chamfer distance. Otherwise, you can even evaluate the Hausdorff distance. It's okay. You can do whatever metric you want. For some reason that makes sense because it's easier to evaluate. People use chamfer distance. I don't know if you know about it. And so that's what we do. But visually, it's clear that it's a better mesh. After that, obviously, depending on the metric, the notion of better is really strong or a little bit weak.
Thank you. Very well. I was maybe a very genuine question about discretizations. You've talked a lot of it, and then of course there was geometry discretization in space, but there is also discretization in time and so on.
Yeah, the mechanics.
For me, what you experience in protein dynamics, talking about that. Because here discretization is really challenging. These dynamics, protein sometimes the library for a long time in some space and suddenly from source to jump to another mega surface. Here, discretization, if you compare the time between this and the time between jumps, it's 1 to 10 to the power 6. So how does it remember if you experiment about this changing in scales of this? If you discretization before all that and you will never get there.
So I have zero experience on this. What we did in the molecular dynamics case, we took the simulation of DNA and the ligands, whatever they call it, linking the two strands of DNA. And people were doing this with a particular integration method. And we said, okay, we can rewrite this as a symplectic method with, long story short, with exponential of matrices, etc., so that the time step that we could take was something like 80 times larger. So we got a speed up not of 80 because we use exponential of matrices. So I think we got a speed up of 20 or 40. But I've never really tried on proteins and this problem of having to compute for a long time before it jumps. So I have nothing to say about the exact question you're asking. We just use molecular dynamics to prove that if you use a symplectic integrator with some bells and whistles to make it able to do bigger time steps, it works and give the right result just faster. It does not answer your question at all, and I have no clue. Okay. By the way, I would be extreme. I mean, people are already doing this, but I'm guessing that machine learning has to play a role in this because detecting this kind of big jumps seems like at least they could pre-chew the computations for you. Right. Right. Absolutely. Thank you. Yes. No, the vector field. You're right. So I went very fast. Obviously, that was just to say you don't need to do appraising just of the SDF. You can do other type of appraising. So you're absolutely right. What we learn here is how to appraise the velocity field. And the idea is, the velocity field is satisfying Navier-Stokes. So again, Navier-Stokes is a local condition, right? And so our point of view, at least in this work, was to say, because it's local, that has to be true everywhere. And so we can try to take a small window, typically 5 by 5 by 5 or 8 by 8 by 8 of grid nodes with the velocities on these grid nodes, force grid nodes, and then try to learn how to appraise it to a finer simulation. And so that's what we did here. We use actually a dictionary-based appraising, which is very different from the previous method. The previous method, we said we want it fast, and we don't really care. There's no physics, right? So we don't really care about the accuracy. We just want an appraising that's really fast. Here, we cared more about the physics, so we did actually a little bit slower using a dictionary-based learning, L1 minimization, etc. But entirely by learning how to appraise a little chunk of velocity vectors from a coarse grid to a fine grid. And then once you have that, you can use it on any big grid because you're going to use the same little network to learn how to appraise locally the vector field that you're dealing with. Thank you.
Another quick question. Excuse me.
Yeah.
I give keynote tomorrow. Can I quickly test the
Yeah,
keynote?
of course.
Okay.
I need to reopen it.
Yeah, sorry.
No problem.
So it's Let's put this in here. You can use this.
Oh, okay, fantastic. Maybe I'll give it a quick try, but yeah, perfect.
You can use this.
I think this one is fine. I have a,
Oh, yeah, okay. I hope it works. No, we should press this. Where is this? Okay.
excellent. Looks very great. Oh, fantastic. Thank you.
Yeah, yeah. Okay. So let's open your this one.
Yes.
Okay.
Uh,
There's also a pointer if you want to use.
I think I have it. Just update it. So,
Okay.
so can I?
Yes, let's use what do we need?
So, so Williams. Oh, take. Williams, I'm just taking the problem.
For you?
Yeah.
Okay.
No, no. I can something's there problem.
Actually, live stream of this conference and also some of the our people taking photos.
Shall I give you my camera?
I have tested, but after
Okay.
I don't. Is that
Yeah,
you can open this one?
so how can I?
This is the laser.
Yeah.
And this is also the next and previous page. But you should open this first.
Yeah. Let's press this one, right?
For me here, rather than
Oh,
wow. Press. Yeah. Oh, this one. Kapalı mı açık? Ya şarj oradan geliyor. Bir sonrakine bakarız. Bence sen şimdi daha gidiyorsun. Şimdi kapatabilirsin mi? Tamam.
Just do so. Actually, do you have on tap on video recording on YouTube? Okay, so if it's okay, the YouTube work for me sound. You don't use it all that. Just resting so you will not show up. So just randomly doing something. Okay, we will already experience behind the sketch one. Thank you. I didn't even Efendim abi, oldu bir seçim şöyle bir arkadaşlar. rate from the exchange. Exchange is there is exchange for moving on to the quality of the I think they are
in the technical form, early. So, it's well up and everyone practice is very nice. Following very good stuff. So my name is Silva and I'm from Canada. Taking a jet that 2016. But yeah, so this is the this thing that you can share. Also, this of this session, which is technical design and manufacturing. Yeah, very distribution and all surrounded bed, manufacturing field topics. So what can you be this? Yes, kind of otherwise the way more so but only every so many things completely need to work on the question. Otherwise, you find that you not the um, yeah. So I'm going to is use the shape of from input or input and loads of estimations. So all the
All right. So, hello everyone. Can you hear me? So hi everyone. Um, so my name is Joseph Jagodi, and I'm here to present our paper on part orientation views shape optimization for 3D printing. So I'm sure most of you have seen 3D printing, and some of you have probably used 3D printers. So when you use commercial 3D printers, most of the time you need support structures to print overhang features of complex models. So here you can see um, the result of armadillo model, and you can see when you print the model, it requires lot of support structures, and at the end of printing, you need to remove the support structures. So all those support structures are important to prevent failures. It increases the print time and material waste. So one of the main challenges in optimization, the design optimization, is to find ways to minimize support structures. So to do this, we have several variables available in the design space. Now, for instance, you can change the part orientation and you can change the part geometry. In part orientation, the idea is quite simple. You take a set of samples on the unit sphere, for example, and then you can change the mesh orientation and you can find the best orientation candidate that minimizes the support volume. Because depending on the orientation, the support structure volume will be different. In part geometry, you can see a simple example again, which requires support structures for the original geometry, and you can change the geometry into a different shape, which requires much less support. But the problem you can see is that the deformed geometry is quite different from the original one. So this type of large-scale deformation might be inapplicable for these complex models. For instance, the Voronoi sphere and like the knot model and complex mechanical parts. So the idea is to find shape changes that are as close as possible to the original geometry. So when you think about the part geometry, it's quite important for 3D printing applications. For example, several local geometric optimization methods were proposed to improve the structural strength of the 3D printed parts. And there have been some cage-based shape deformation methods that minimize support structures. but you can see those methods deform the shape globally. And there have been also other methods to improve the balance of the 3D printed parts. And there are lots of other applications of geometric optimization. So in general, these examples show that geometric optimization is quite useful to improve the 3D printing performance. Now, in general, the existing methods treat part orientation and geometry as separate variables. So the main question we have is to see if we can find the best, if not the corresponding pair of part orientation and geometry to minimize support structures. And the next question is, can we optimize directly on triangle mesh models, because the designers prefer to work on the triangle mesh models. So for this, we propose an alternating optimization method, which change the part orientation first, and then compute the geometric updates for that particular orientation, and then kind of repeat the process until we meet the termination criteria. So the idea behind this alternating optimization is quite simple. So we convert the joint optimization into a set of simpler subproblems. So before we move to the optimization, we need an objective function. So we define the objective as a combination of overhang faces and support structure volume. So here you can see a set of examples of part orientation optimization using different objective functions. So you can see what happens when you use support structure volume only. The number of phases. So even though the volume decreases, the number of overhang faces increases. So in our case, what we try to do is to minimize both the overhang faces and the support structure volume. So how we compute the volume is by projecting the faces onto the build plate. And from the graphs, you can kind of see our method is quite efficient compared to the Rabies approach, and it gives a quite good approximation. So the first step in optimization is the part orientation. So we use Fibonacci sampling to get the orientation candidates on the unit sphere. So again, the idea is quite simple. We pick the best orientation vector that minimizes the support proxy function value. And the users can pick different number of sample values. And here you can see the effect of sample values on the optimization time. So the next step is geometric optimization. Here the idea is again simple. What we try to do is to project overhang faces onto overhang free configuration. So for each overhang face, we compute an overhang free plane, and then find the difference between the current phase and the target phase through a rigid transformation. So that provides the phase level change, as you can see. And then for the vertex level change, we propose a salient feature aware projection method. The idea is to minimize deviation in salient regions, salient but overhang regions. So if you look at the full shape energy, it's a collection of few energy terms. So the first one is the projection energy, which is the difference between the current vertices and the projected vertices. And if you look at the smoothness energy, it helps us to ensure the vertex deviation is smooth. And then we add the support volume as well. We have several termination criteria, but the main one is the deviation from the original geometry. And you can see the shape change between the original and the optimized one is quite smooth. And also depending on your 3D printer, the overhang angle might be different. For example, if you use a high-end printer like Bamboo, FDM printer, you can print up to 60 degrees of overhang angle. So here we show that our method can be run with different overhang angle thresholds. And if you look at the results, first we present the alternating optimized results. So these have been optimized using orientation and geometry both. So you can see the difference between the original and the optimized versions of the armadillo. So there's a significant difference between support structures. And this is the knot model, which is a quite complex one. And again, you can see the difference in the support structures. Yeah. And then our framework can be also used as a geometry only optimization. So which means we take out the part orientation, but simply use the geometry. Choosing between these methods depend on your part and its complexity. For example, for models like these, hygienist models, alternating method performs better because it helps to reduce support under lower deviation. So you can also see some sort of difference between the support structure volume uh, between the geometry only and alternating optimized versions. But in general, both the methods are effective in producing support structures. So for models like Kitten with a flat base, users prefer the geometry only optimization. So we have the original one and the optimized one. And again, you can see the difference between the structures from the clean models. But again, you can see the effect on surface feature distortion if you look at the optimized version of our model. So to minimize this effect, you can fix the important regions of your part. For example, the functional regions of your part. So for instance, in this example, we fix the face and the base of the Venus model before the optimization. And as you can see, it helps to minimize the effect of surface feature distortion. From the right-hand side, you can see the printed versions of the original and optimized versions. And if you look at the print times and the weight, you can see our method is both applicable to different support structure types. So in summary, we propose an alternating optimization method to find the best pair of orientation and geometry for 3D printing. The main advantage is our method is effective for a range of complex models, and our method can be used directly on triangle mesh models. Our method is also quite fast, and you can see the results from our paper. So one of the main limitations is, as I showed you earlier, the surface feature distortions from the projection method. And it can be quite challenging to optimize high resolution mesh models using this method because it increases the size of the linear system. But these limitations have been addressed by our recent method. So I will take 2 minutes to explain that as well. So in the new method, we learn the shape deformation through a neural vector field. So the difference compared to the previous method is that in this method, the shape change is differentiable and continuous. And we also introduce a post-affine optimization method to efficiently optimize high resolution mesh models. And you can see the difference between the original one and the projection based method in our paper and the neural shape. So you can see the face features have been preserved in the neural shape. So for those who are interested, I invite all of you to have a look at the paper. So thank you.
Thank you, boss. You into account some physical constraints.
Uh, yes, so actually this is one of the of one of the next steps that we can consider in the optimization. But to have that physics constraints, we might need to extend for like a full volumetric model to find the like the finite element computation. So that can be one of the future steps. Yeah. Thank Thank you for the question. Yes. No, no, no. Sorry. No, so the we compute the normal support structures only. Um, so right now the for the optimization for the proxy function, we only use the normal support structure types, but for just to show that it's effective. Trace of the types, we just show some examples, but it's not guaranteed. So because we are not using reduce that the thank you. For instance, I think can be good if you can have a differentiable summation of the results types, for example. So then we can integrate into the optimization and then run through the same pipeline. So that the uh, future steps. Uh, yeah, okay. That, but yeah, maybe I'm not very sure as well, but yeah. So like what kind of paths are you doing? Yeah. Yeah. So I think, like for example, in the neural shape method, we don't use any kind of like except for volume. We use the overhead phase as a variable, and then we show that we can actually minimize it by completely reduce constructions like overhead phases, because overhead phases generate constructions. So if you can get rid of the overhead phases, then you can have to get rid of volume. So I was my answer. Focus on the overhead phases. Maybe not touch the Thank you so much. If no other questions, then yeah, let's thank the speaker again. So the next presenter is Lucas Rodriguez.
and he is going to present a lifetime-based generated design of 3D printed bearings. While he's setting it up, I just want to ask again whether the authors or presenter for the third paper is here. So I guess we guys another 7 minutes. Okay, yeah. Yeah, the floor is yours.
Thank you. Yeah, so um, today I will present my work about lifetime-based generative design of 3D printed bearing. I did that book with here, and I am currently in postdoc in Concordia University in Montreal. So today I will present a work that have some motivation. The basic motivation was that bearing is an ubiquitous mechanical standard component present everywhere. So basically from a motor to a wheelchair, and basically every system that have a wheel in the world have a bearing inside. This is a really standard component made in often steel, but sometimes supply can be severely limited because of the environment, because of the context, because of a lot of things. For example, the space, for example, during pandemics, sometimes it's not possible to just deliver a bearing somewhere. So we want to develop something to to replace that kind of bearing temporarily in order to make and manufacture directly the bearing from his own 3D printing, 3D printer. So here is the research problem. How to develop a fully 3D printable bearing design methodology designed to be manufactured locally with affordable printer, because we wanted to make it with the more affordable printer, the basic one made with plastic and PLA. We wanted it to be assembled on site without the need of a complex tool, for example, without any assembly, without any screw, without any nuts, for example, and adaptable to local constraints. So we have special constraint. We want an optimized design that maximize the lifetime of the bearing. So that was the research problems, basically how to make a design of a bearing that maximize the lifetime, but being in PLA, 3D printing with affordable printer. So here is the research problem. For the state of the art of in the literature, there is a lot of paper on classic steel bearing lifetime prediction. Of course, this is a really studied field. It's for a long time. It is studied the lifetime prediction of standard component like bearing, but it is always still bearing. There is no design optimization. I mean that the geometry of the bearing is really standard and always the same. So it's really the lifetime is really predictable, which is really different when we 3D print it. There is another field which is classic steel bearing design optimization. It is also steel bearing and with very limited geometry. For example, they just focus on the inner ring, inner race, or outer race of the rings. This is a really limited geometry deformation because of the manufacturing process, because we want it to be ball bearing and really manufactured easily with steel. So that's why the design optimization is as a really small design space. And now for a few years, there is 3D printing during experimentation. Um, in some people generate some new design and try to experiment and try to measure the lifetime of the building and measure how it failed and how at what time. But there is no design optimization of it. They just test design directly and no lifetime prediction. So that was our goal to make some methodology that can predict the lifetime of the geometry and optimize the geometry to maximize the lifetime. So at the basics, we test a lot. We design first test bench and test rig with a model to test all the bearing and measure the lifetime of bearing and the radial load. And actually, it was quite surprising that there were more than one type of failure that can exist. There were blocking failure, which is basically the internal rotation of the roller that can block together and block the rotation. And this is not really fail as the bearing doesn't break, but it's blocked the system, so it's considered as a failure for us. There is the breaking failure, the most famous, just the roller breaks during the rolling, and then the dislocation. It means that the roller goes out and escape from the rings because the geometry is too flat. So the overall idea of this work is that for each kind of failure, we created a score associated of a geometry that is used to predict the lifetime. And then we correlate the lifetime with the experiment, with the score that we designed. And with that, we created a design space for building construction. Like this, we were able to optimize the geometry in the design space to maximize that lifetime. And then we get some results of optimized geometry and we're able to compare it to state-of-the-art geometries. So I will go through all the type of failure and say how we designed the score for the geometry. So for this collocation failure, the problem is when the roller escaped from the inner and outer ring. So for that, we just take into account something that we call the science abrasion field, which is basically just a sign distance field, but in one direction. Because as our roller are always in the real shape of revolution, so we can simulate it. Just go through through this this formula. And we tried to simulate the abrasion of the plastic during the experiment because there is only a decreasing of the plastic during its roll. And we simulated it with that oriented silent distance field. And like this, we can create a field that represent the collision of between the roller and the rings. And like this, we can measure the the dislocation of the roller to the ring. So how we measure that? Basically, we we make a path for the inner ring, and we try to make a path minimizing the collision between the three components. And we see the minimal energy of collision that it takes. We designed the score based on that maximal energy, which is 1/1 plus the energy, because we want it to be between 0 and 1, and the Taylor geometry has a score of 0. So that is for the dislocation failure. I will explain later how to to modelize the lifetime. For the blocking failure, this is a bit tricky to explain, but this is an internal rotation because there is clearance between the components, so there is an internal rotation of the roller. And when it rotates, it's blocked together. But first of all, we have to know if this rotation is feasible or not, and we will quantify how the roller can rotate in that direction or not. So like this, we can just rotate the roller until collision with the other ring. And for example, with complex geometry like the Hubble geometry, we have 90 degrees of rotation. It means that the roller can completely rotate internally without any collision. So it means that it will block directly because of it. So that's not a good geometry, and we prefer that the bottom geometry that's shown here. To see if it will block or not, we have first to measure the distance between the two rollers in function of the rotation of the two rollers and also the clearance between those two. I will not explain how to measure the distance, but here it is. And the problem here is to see if the point zero is a local minimum. I explained. We want the bearing to be to be stable when the two rollers are exactly at zero location. Because when they are not rotated, we want the bearing to be stable. So we don't want the roller to rotate automatically. So when we have the graph of the distance between the two rollers and the orientation of the two rollers, we want it to be stable at the 0 point, so it means that we want the 0 point to be a local minimum. And like this, we can directly check this with the by verifying some trajectory in that surface, and then create the blocking score, which is proportional to that local minimum. So how to escape from this score or not. And the harder it is to escape, the better it is for the baby. That was for the blocking score. For the breaking failure, this is way easier because this is the most studied failure in the literature. So we can first simulate the maximal stress in the roller thanks to Earth's contact. And then we have the relationship between maximal stress and lifetime that follows a Weber law, because this is how it is today in classic steel bearing, and we reproduce it to plastic bearing, considering that it will follow the same mechanical rules. Adjusting all the coefficients. Actually, as we will see later, it works pretty well. So that's how we designed our score for breaking. So now that we have all these three score, we can modelize the lifetime of a bearing. For this, we test a lot of bearings in the test bench. We adjusted the coefficient considering that the equation would be in the type of the balloon with a weight and exponent, as the breaking failing law as shown and previous experiment shows. And we made the assumption that all the type of failure follows the same types of equation. So we have the coefficient W and N, which is to modelize the lifetime. But we have also two other coefficients, which is eta and beta, and they are for taking into account the probability of failure, because we cannot predict exact lifetime duration of bearing. We will predict a distribution of probability of failure, because it will not fail at each number of cycle each time. So that's why we have all the coefficients beta and beta. And for which we did a lot of tests to adjust those coefficients. To illustrate the fact that the probability of failure is important, for wrong profile, the given probability of failure, we can get the number of cycles before failure. Then, for example, this kind of shape of roller, we have this type of brackets which shows the cycle of failure given the probability of failure. So we can see that given different probability of failure can give a different number of cycle of failure before failure, of course, but also can change the type of failure. So it means that the ranking of the profile can vary depending on the probability of failure that we want. So we will set it at, for example, 50% or 90% and set it and do the optimization given that probability of failure. So the design space definition for this building is just a B-spline curve done with some control points. It is the blue curve to the left. And given this control point, we can get the busy curve and we apply the symmetry, order symmetry, and get the remotion of the ring and the ring. We get the complete geometry of the ring in order to make it after. And we can get the exact number of roller in the bearing by adjusting some measurement. Basically, this is the distance between the z-axis and the center of the bearing. And by adjusting this length, we can exactly get exact amount of number of roller because it must be taken. So anyway. The design space definition have some design constraint, for example, the minimal thickness of the outer ring, the inner ring, and the minimal thickness of the roller. Done with experiment, because if it's too thin, it means that it will break even before beginning to roll. Also, there is the maximum angle of the printing, which has exactly what the previous presenter said. So we have to get this B-spline to respect that constraint. So we set all the values at the bottom. And now that we have everything, we can begin to optimize the geometry. So we create a curve with Bezier coefficient. We simulate all the lifetime the coefficient we found experimentally, and then we get the minimal lifetime given the 3 lifetime that we get, and we just take the lifetime, the parameter font with the best lifetime, and then apply a genetic algorithm in order to optimize and maximize the lifetime. So here are the results. We saw that blocking failure encourage a flat surface, which is quite normal because it means that it will be stable when both roller will be in correct position. Dislocation encourage radius variation because it will be less dislocate when it has a lot of variation, and breaking encourage large minimal radius. So given all that, at the end, we see that the best types of roller geometry is things like the blue one at the top. And the state-of-the-art bearing was tested on the test bed under your nodes in order to compare. And we multiplied by 20 the average lifetime of the bearing. So actually, that's a lot. The limitation of this work is that we consider only pure radial forces and no axial forces, which can vary a lot the type of failure. There's only revolution, and we consider contact over all the length of the So that's why the future works focus on enlarged data space with geometry, which is also a really encouraging design without any revolution or that like this we can explore widely the design space because additive manufacturing opened a lot of doors in the design space to a lot of geometry. So yeah, thank you for your attention. Questions?
Very nice talk. Thank you. So are all rollers online or does your framework also support maybe component rollers or even
Yeah, by congruent, you mean contact between the
geometrically identical rollers?
yeah, they are all identical. Yeah. For now, they are all identical because, of course, the maximum radius must be the same in order to be in contact with the inner and outer ring. But that's also, yeah, I'm just thinking at the same time. But I think that if the geometry of the curve differ, it means that sometimes there is no contact with the outer ring or the inner ring. Or
maybe still be in a contact, but maybe for this okay. You have two different geometries. I help a bit in this block points.
Maybe I don't see what do you mean by congruent geometry.
If you have identical geometries, you have certain condition to avoid conflict. And if you have, let's say, both rollers of different geometry and even of different geometry, you have kind of not just a single profile instead of a particular optimization, but you have two profiles, two rotation shapes.
Okay, yeah. Yeah, for now the methodology doesn't allow that kind of shape actually, but it could be another future works to work in, even if it's revolution shape. Yeah.
Thank you.
Thank you. Very, very interesting part. So your material is plastic. Addition, what if we do additive manufacturing with metal? That's
Yeah.
also possible these days.
Yeah. I think it will be really interesting, and I think the methodology can be transferred to metal. We didn't test how actually, but I think that everything we made, we took into account the clearance and everything. So I think with metal, the clearance will be maybe wider or maybe not. Just the coefficient will be different. So I mean, the interesting part will be here, or the coefficient will change with metal. But I mean, all the other studies, the type of failure, maybe the failure will differ. Maybe but I think that theoretically it shouldn't change. So everything can be transferred to metal manufacturing, and it will be also really interesting because it means that the lifetime will be way bigger. But the controversy is that it's not manufacturable everywhere because metal additive manufacturing is key. So that's why we choose to focus on PLA, really cheap material.
So it seems to me that you utilize genetic algorithm. Yeah. So right now, even commercial software has lots of genetic algorithms. Did you try others?
Other optimization, yeah, we tried. We found that the best one was a classic genetic algorithm, and also it's very common. We use geometric algorithm for generative design, and it fits very well because we have to explore really different geometry and go deeply into that kind of geometry. And also when we do mutation and crossover between geometry, it means that the best geometry will be between the best. I mean,
So you penalize the designs that doesn't satisfy your knowledge.
yeah, of course. Yeah, no, I didn't analyze. I just cut it off. So I didn't took into account the design that didn't respect our constraint. So that's why I showed just the first generation is the generation 3 because the 1 and 2 is out of constraint, so they was not even shown.
Thank you very much for your presentation. Actually, we're planning to do metal printings, roller lyrics in the future, so it's very interesting for me to see this. One question I have is considering the lifetime, have you thought about the beer properties of beers? Because especially by plastic, I think a beer might be quite drastic, but also in France, for instance, so of
I am the
again, so, sorry. Did you get the question?
are you talking about the lubricant?
Yes.
Yeah. No, we wanted to be the as a first study on it to be the simplest way. So without lubricant, with the cheapest material, with the cheapest printer. That's all. So we didn't try the lubricant because also the thing is that it's really hard to do a waterproof cage in 3D printing. So that can be movable. So that's why we discard this solution, even if we can put some lubricant, some grease without any waterproof cage, but it means that it will escape, and at one point it will just live a longer life. But we just made the assumption that the best design, the optimized design in the dry experiment will also be the best design in the lubricant environment. But maybe that's not true, and that's why we have to do further experiments.
Okay, I have a question. So very interesting both the work. So I'm wondering, did you try like a bearing model to print by using some commercial 3D printer at the any cubic or any others? Because that my son by chance to print some bearing models by using some commercial 3D printer. Looks like there is no challenge like what you show. For example, like the blocking, breaking, or dislocation. So I'm wondering, is there some challenges because we are working on some very spatial bearing model? I'm just curious.
You think you mean is the constraint will change if we change of 3D printer?
No, I mean, for example, we download some bearing model online and use in commercial 3D printer. Yeah, they can print.
Yeah.
And seems no issue. Yeah. I'm curious because your bearing is more practical and realistic, or I don't know. Yeah, it looks like.
Yeah, no, but it's not just about lifetime, right? If this left the bearing, it revolves during 100,000 cycles. So it means that it rolls a lot. But it's nothing compared the optimized geometry. I don't know if it's answered, but I mean, if you just it's not optimized data. If you just printing a sphere with a 3D printer, it will work, of course, but it will vibrate, do a lot of vibration. Dislocate really quickly compared to that kind of geometry that doesn't have this kind of problem.
Okay, thank you.
Thank you. I guess the question is also related to which printer you used to print it, and also like what condition you used to do the testing.
Yeah, so we did all our experiment with Ultimaker Cure because we wanted to be reproducible and we wanted to do everything with the same printer to be the more predictable and be comparable to the other. But we also, in my side, I did also the test with Anycubic, so with Creality 3D printer, and each time all the condition we have to set is the clearance. So it means that, and also the angle of printing, because there are some printing when there is less layer, we can have a better angle of printing. So these two parameters have to be set when we change the printer, but that's this is really easy to set in the framework.
All right, thank you. So no further questions. Thank again for the speaker. Perhaps I'd ask whether the front center is here, the presentation for the flow paper. Our last presentation for the session one is about visual repetitive different generation of spot-free stochastic porous structure represented by Xiaopan Liu. So I'll give the floor to.
Thank you for your introduction. Good morning, everyone. My name is Xiaopang Liu. I'm honored to present our work visual probability-driven generation of support bricks, stochastic porous structures.
Are all the speakers here? Speakers for the second session, please show up. Missing two speakers. We are about to start. Okay. So this one is the first session for Shape Modeling International. This session is on discrete shape modeling and analysis. I know it's straight after lunch, so come on. The first speaker is Suvedo Hanti, and he's going to talk us about his work on infinite element method-based discretization of a Hamiltonian operator on triangular meshes.
So right now, on and present here my work in my internal purpose discretization of Hamiltonian operators, triangular meshes. So one thing, particular techniques, as well as one university analytic here. So this work has been done by me and my guide, Dr. Radford, economic Marshall. So the motivation for this work is a major source of intrinsic and extrinsic features of 3D objects represented by the sort basis for forming the object are differential operators and their spectra. So several attempts have been made to capture the features or information that is intrinsic to the software, such as mean correction. The spectrum of the operator like Hamiltonian, Laplace spectrum, and they are operators. These related to Neumann operator have been used to perform extrinsic self-analysis. So Hamiltonian operator has been used for various applications like partial sequencing, complete manifold modes, and Hamiltonian modes and maps for correspondence. For computational purpose, all these operators tend to be discrete, so that they can apply to discrete representations of 3D objects. So these are the references where this in this paper, we have contributed an internal method which discretization of Hamiltonian operator and regular method. So the discretization is symmetric first semi-different. And so accordingly, we will get orthogonal eigenvalues and non-negative eigenvalues for precise linear basis functions. So we got a higher accuracy than existing methods in solving Poisson equations. And the computational complexity is comparable with the existing discretization. Right? So equation 1 here presents the Laplace spectrum operator, which is the generalized for Laplacian soft surface S in R3. And this G and this superscript G that is the element of the metric on S, and this superscript is the inverse of G, and the determinant of G is the determinant of the metric matrix that captures the operator captures the intrinsic information, intrinsic geometry. Now, based on that operator, we have another operator which is Hamiltonian operator, which is sum of the Laplace spectrum and the differential function with diagonal operator, which is self-adjoint on end functions on the surface, and then the eigenvalue of HF is equal to EF, equation 3, provides the spectral basis for self-analysis. Now, this here represents an operator equation. Then we can convert it into an algebraic equation by like writing f as a linear combination of the finite element basis functions. Then what we are doing is from equation 4 we are converting it to an algebraic equation. Equation 6. So we are W and A are the stiffness and mass matrices.
But in the here in the previous slide, in equation 6, the first term is already evaluated in the lab when we're solving the Laplace equation. So the W matrix is already evaluated. So the next term is only remain to evaluate in the Hamiltonian eigenvalue. So, but where we can see in the paper 2, they have approximated in B, Z, B, I, the second term as A, I, Z, B, Z. And they got the corresponding discrete Hamiltonian problem as in equation 7. And the discrete Hamiltonian operator they got in equation 8. And we are referring it as H direct is equal to W plus 8 I. And so similarly, this paper in 7 also they have approximated the mass matrix to long mass matrix. So they got equation 10 as their discretization. So you can remember the diagram from a long way which is in our order work. So these two are the existing from discretization. So but the discretization doesn't agree some properties of the continuous Hamiltonian, and another one is somewhat not accurate in terms by solving the Poisson. So where we provide discretization which satisfies both the conditions properly. So what we are doing is we are writing the potential function as a linear comparison of piecewise basis function. And in equation 11, so we talk accordingly in 3D tense. Q I Z K, which is Pi is a BK. So inner product over to this. So and once we sum it over one indices, let's say K, we will get the order tensor over matrix R. Okay. So we got in equation 12 our discrete eigenvalue, the discrete eigenvalue Hamiltonian formula and the discrete Hamiltonian operator in equation 13. So this is the like the support for the this is it from this picture one can see that these are the support for the piecewise linear basis function bi, bz, and bk, and because of this definition of the piecewise linear basis function, we have to evaluate only in the tensor this q I z k in equation 11. Only these three terms q I z and I z k are need to be evaluated. Other terms will be zero. So when they have a common overlap or not a common overlap. So because of the property of Q is a sparse matrix. So we can get from the explicit closed form of the forms of Q in equation 14, 15, and 16. So now consequence Q R of tensor. Similarly, as R is considered from Q, so it is R versus A in the loop case. So we can compare the computational complexity with the existing methods. So this is a special case of the three domains. With one dimensional case, we can see if we don't integral by the piecewise linear basis functions, we will have in equation 17 the closed form of the tensor q I z k, and on this is the piecewise linear basis function independent in R. So here our matrix constructed matrix R is triadic, but it is not eligible for a mesh. So these are some theoretical properties of the proposed discretization. So the proposed discretization, the matrix we constructed is symmetric of symmetric, and the spectral property is saying that if we have a discrete Hamiltonian eigenform, that will give the generalized eigenvalues are like non-negative, and they will be real, and we will get corresponding orthonormal eigenbasis. Okay. And the lemma last one is saying if the Laplace spectrum operator is symmetric partial symmetric, right, then the generalized eigenvalue problem of x down and x up then non-negative. So the proof of these terms have been discussed in the paper. Can so we're doing some doing the we're now showing the spectral property what we discussed in the theory by experiment. But here we are taking in diag and psi proportion. The proportion discretization we are taking all the eigenvectors what we got by proposed method, and this diag we are taking all the eigenvectors what we got by the diag method, and we're computing the Gramian matrix which is P diag and P proportion. Okay, we can see here for this potential function in the left hand side. This is the step potential on a 1D interval case where the points are non-uniform. We can see that in the right hand side, we are computing like 8 number of eigen functions So the Granite matrix should have, if it is satisfying the orthogonality property, should have at most 8 number of non-zero entries, which is in the proposed method. The line which is in the proposed method in the line, which is having 8 long. But in the Gaia method, it is not the case where I have more than 16 non-zero entries. So it shows that this Gaia method is not orthogonal, not providing orthogonal basis, but the proposed method is providing that. Similar experiment we have done for different potential. One is the linear potential and another is the random potential. So we can see how the method is consistently providing orthogonal eigenbasis, but the diagonal method is not. So we're doing this, what we have done in 1D, we are extending the same method to this. Here we are taking initial input 1 MS with this many number of vortices and faces. So also an Hamiltonian mesh. So where the potential here is smooth, here the potential is strike potential. So we can see we're computing a 100 number of eigenfunctions. So over here we can see the 100 elements, the diagonal elements are present in the proposed method, both the faces, but in the diagonal method it is not. As we are increasing the error tolerance, so that means out of how many number of non-zero entries, like above this error tolerance from 10 to the minus 10, 10 to the minus 1. This is like showing 10,000, but here it is 100. So similar experiment has been performed for another mesh. Here we are proposing on we have done experiment on 17 methods of self-reading data set. Okay, we can see clearly the output what we have done. Here is showing by this experiment the indefiniteness of the direct method. So for this left hand side, the potential function, we are getting the eigenvalue is non-negative, smallest eigenvalue is non-negative. For the existing method, it is there. Which should not be the case because the Hamiltonian is a positive, like a elliptic operator. So all the eigenvalue has to be either 0 or positive. But in the existing method, we have written a negative. This is the corresponding eigenvector. The necessary subset participation but the potential is constant. And we are assuming 0 if the mesh has been found. So the proof is already and now we are showing the complexity. So complexity for both the existing method and the proposed method. The last method is the another existing method. So the proposed method is what we have proposed. You can see both have same number of the same computational complexity and the memory consumption, which is order of n dB. So we can solve via experiment how much time we are taking while we are computing the eigenvalue problem, but we are solving the eigenvalue problem. So here you can see for different type of meshes started from 5,000 vortices to 72,000 vortices. The computational time is approximately same, but in proper method we are taking some more time because we don't have a here we have a diagonal matrix, here we don't have a diagonal matrix. So that's why this is taking somewhat more time. But the order we can see theoretically both are the same order. So this is the so but we are showing that the proposed method is more accurate. So actually with respect to the analytic source. So you can do this. So now I'm showing the comparison with the analytical source. So when we are solving the eigenvalue problem, and we can only find out its analytical source of the constant, and so we have found out its analytical source on the unit interval and triangle here. So here you can see like the analytical solution is in blue is there, and the proposed and diag method is overestimating, and the long method is underestimating that. Okay, but the partial portion of the eigenvalue are same for all the methods. Okay, and so this is for 1D, and for mesh with respect to this eigenvalue, we also have the same behavior. Here blue is the analytical one. This is overestimating. This is underestimating. So here we got also the error in eigenfunctions. when we can solve it on a on a on an interval, we can see that the proposed method in black is having less error, and the direct method is having more error. And the error is decreasing as we are taking more number of points, which is in x-axis, and this is the y-axis is error. So we can see the error gap is increasing as we are increasing the index of the eigenvalue. The simpleness for comparing the error for a mesh. This is for one thing, this is for mesh. So you can see for different L, here we will get the analytical solution and spherical harmonics. So for different L, we can have in blue we have less error, but in orange color it is having more error in the long method. So and it is decreasing as we are taking more number of points on the sphere. So from started from 40 to 10,000 pieces. So now doing it theoretically, well, we are coming to Poisson equation with Hamilton operator. So the Poisson equation in equation 19 is given in this, and this is the weak form of the Poisson equation with Dirichlet operators. And we can have if this is the weak form, then we can have the solution is exist and unique that has been proved by this following people. This the proof is happening. And now we're comparing the solution of the discrete method and the analytical method. By first we can solve it by taking a potential function constant. This is the right hand side. So we have the analytical solution, and on a 1D interval we are comparing the solution. So you can see in blue the error in long method, and in the black the error in the proposed method. Proposed method are always less for this right hand side function, and this is the potential function. If you are changing that also, we are having better result. That means the long method is having more error, is having less error. Also for a spherical harmonics, so this was for one thing. Again, this is for MS. This is the right hand side function and different potential function. Also, we are having in blue is having more error, and in black is having less error. So the conclusion is we propose a discretization of the Hamiltonian operator and triangular mesh with strong theoretical analytical method. The eigenfunction often from the proposed discretization can be used to compute the heat current energy with solve such pictures for the partial set mixing. So theoretical convergence analysis of the proposed method is with analytical solutions. Another feature of all this convergence analysis is shown and numerically. Theoretical analysis we have not done yet. So if it's able, we'll include this discretization for particular applications such as same method to demonstrate the practical utility of the problem. So present.
You are perfectly on time. So, any question?
So you talked about that shape matching application, right? Do you think it's a local shape matching or it's a global shape matching that you're talking? You talked about partial.
It's a local thing.
Do you have any result of
We are working on that now, so it's not complicated. So that's why I'm not.
I see. Okay, that would be interesting.
Yeah.
Thank you for this very nice talk. And I would like to know if you tested the robustness of your approximation with respect to the quality of the triangle. If you have very slender triangles and somehow maybe you have to test such things.
You're saying like
So I mean, your discretization, you can apply it for any kind of input mesh. If you have a mesh with very regular triangulated triangles, or if you have a mesh with badly shaped triangles, maybe there are the always marginal. This is what I
yeah. So we have so that we have tested about different type of like having less number of triangles towards more number of triangles. Whether the discretization is final or not, the method is working properly. But what you are asking, I think, if the like the mesh has a hole or something like that. So for that type of mesh, we have not tested. We have tested with like completely smooth and closed manifolds. So we'll do that. Thank you.
Any other question? Okay, so that's the speaker again. Thank you. The second paper is parametric garment design with explicit and non-fairness control. And the speaker is Christian Pato. Okay, can you connect his lab? Is it okay? Yes.
Okay. My name is Christian. It's very nice to meet you at the conference. I will just briefly introduce myself and some of the people I've worked with. So I'm currently postdoc at the University of Zagreb, and previously I was postdoc at the TU Dresden, where I mostly wrote the paper. My supervisor was Stefan Buchholz, and these other people were collaborators on the paper, since this was basically 2 years of time to develop the framework. So I will just quickly explain the keywords. Explicit and local ease, kind of describe, not really define, but describe the term ease on the garment, and also parametric, because you can control the parameters of the model. So let's start with ease. This is a very simple kind of visualization of what ease would be if we had. So it's definitely the whole project is for the human body and for the garments. So we can assume this is a human body. And the left diagram assumes skin tight garments. So the ease would be basically 1.0, or there wouldn't be any additional material. On the right, there is some ease. So this garment is loose. So this is not a definition, this is just illustration of what ease is. The problem with previous work that we noticed is that usually the ease is a kind of a byproduct. And there wasn't really a way to control this ease. And usually you do the simulation after you do the 2D swing pattern. So you cannot explicitly clearly control this ease, how much material there is certain segments of the body. So we focused on the specification, editing, transferring, and redistribution of ease on the body. This is kind of a teaser image where we show what can do and what we can do with these. On the left, we have specification ease, where we say the sleeves we have a bit of material, and you can see that they are wider. And also the pants, part of the pants, there is more material. As a result, we also compute the swing patterns. Everything is done in 3D, and the final result, and one of the results is 2D, and finally the simulation is again 3D. One of the key operations that you can see in prior work is also transferring these to target shapes. For example, this is an extra large shape, and also adaptation to target pose to accommodate for movement. Prior work, maybe just kind of quickly specify what we built upon. This is the courtesy of Pietroni et al. This animation, which we kind of reuse for our purposes.
So what they do is they enforce the anisotropic scale. So they assume that the 3D and 2D surface and the triangles should have the same elongation. So the 3D triangle should not elongate compared to the 2D triangle. And this is where we kind of generalize the prior work. Our pipeline actually covers the whole design process, which is a unique framework because we start with the body, then we design the garment, we optimize the swing patterns, and finally we drag everything in 3D with simulation. The first step is to design, and we design directly on the body. We have a UI where we start with the simple body model. Simple was done at the Max Planck Institute in 2015, and it was a very famous cigarette paper. We click the key points on the surface, and everything else is parametric, so we can specify all the other parameters such as length and ease on the body in terms of in the form of scalar values. So the first stage is a design stage where we emphasize the parametric part of the design. So we can specify where the seam lines are and what the ease in 3D is on the body with respect to the body. So seam lines, they define also the patch boundaries between the garment pieces. So for example, usually we have the front patch, we have the back patch, and we have the separate sleeve patches. Also the parameters define, as I said, the length, how much of the body is covered by the garment, and also we can define ease, so how much extra material compared to this body surface we aim for. So we can also have extra material, but we can also have kind of less material or stretch. So we can purposely have stretch and tightness. So we can say that this value is a design variable, which is the core contribution. The second part is to actually solve the system of equations to get the swing pattern in 2D. So the idea is to start with 3D triangle on the body and to find the corresponding 2D triangle with specified ease. And we can do that via barycentric coordinates. We do this using barycentric coordinates because the whole system finally is locally globally optimized, and which is you can solve it linearly between the stages, so it's not non-linear, which we wanted to avoid. Finally, we have one energy which we solve for each patch. So each energy solved and because again we want to keep this linearity and avoid complexity because there is a lot of rigidity if we solve everything at once. So three components are key here: the ease component, the seamline component, and the regularization component. The ease component has two directions, which is left and bar. So left could be said as a horizontal direction, and the one direction is typically vertical on body. Seam component enforces the manufacturability of the swing patterns. We want the seam lines in 2D to be, let's say, nice. And there's a lot of kind of conditions to keep in mind for the pattern makers, because finally, if they want to manufacture it, we need to ensure that the seam lines are corresponding well. So we also add a few terms which I will describe on the next slide. And finally, the regularization, which was also very important, is simply analyzing shear for each triangle. Finally, everything is solved as in a normal fashion, starting with the least squared conformal mapping and for a few iterations, and this step actually is fairly fast.
So the scene constraints are important in order to ensure that the final swing pattern is nice for manufacturing. And we decided to have three different subcomponents, which is 2 to 4 length. So the scene lines have to have the same length. That's actually the most important criteria, because if the lengths don't match, then you have a lot of then you have extra material on one side, and this is definitely a disaster for manufacturing. The straightness, so the seam lines, corresponding seam lines should be fairly straight, although they cannot be completely straight, otherwise this is trivial and you cannot really design for a 3D body. And finally, the curvature matching means that concave parts correspond to concave parts, etc. So convex part corresponds to convex part. So these are the three components that we use for seam line matching. What is also very interesting compared to prior work are these two operations which I mentioned before. So these are transfer and adaptation design. When transferring, we want to ensure that the design is same for the reference body and for the target body. The equation that we use is actually similar to the one we used for the reference body, which is one turn with the target, which means that we take into account the anisotropic scale of wave direction for the target body and not for the reference body. The adaptation to new poses is a bit different, but it's actually, so instead of looking at the equation, it's easier to describe it in words. So when we go into the target pose, certain target poses stretch the skin a lot. So we have to take this stretch into account. So what we do is we take the maximum between how much stretch the skin introduces compared to how much stretch the garment, the original garment has. And finally, we have the stretch tolerance, which is important to adapt to target poses, because if we adapt to a very extreme pose, such as sitting or crouching, then there is a lot of extra material. So sometimes we want to say, okay, we don't want to adapt to this very extreme pose, but to adapt partly, which can be done with material stretch tolerance. Finally, to get the 3D asset of the garment, we do the simulation. We finally use Newton, which was at that time, which was recently announced as a new simulation framework and worked nicely. Since we start with the 3D body, we didn't have problems with the collisions, since the initial state is already in collisionless. So it's in the collisionless state when you start with 3D body. So these are some examples of 3D. Okay, now we go to the results, where I show first the ease, which is kind of the, let's say, the core contribution. On the left, we have negative ease. In the middle, there's ease, which is equal to the body. So let's say skin tight, and we on the right we have the ease, which corresponds to a bit of looseness. These are the examples in 3D, where we start with smaller values of ease, and then we go to higher values of ease. You can notice that the arms are moving. This was actually done at the point where we had to adjust for the pose, but later we actually solved this. It just generate another animation. But the movement of the arms is basically just for the purpose of visualization. So a bit of animations for what the parameters can do. So we can change the sleeve length, we can change the shirt length, and we can do some kind of geometric additions, for example, the recline extension and changing the neck position. There are some more parameters, but these are maybe
make sure it was prominent. Then we have the transfer operation, which takes different body shapes, and the goal is to have the same design for different body shapes, from, let's say, smaller bodies to bigger bodies. And you can see that the wrinkle details are slightly different, but the overall material is preserved to the body. When adapting to pose, the idea is to relieve the strain, we could say, so that when the person has a relatively skin tight design, when they sit, they want this design not to stretch too much. So we can adapt the sewing pattern and the design for the target poses. This is the overall quantitative image for the results. And so we have looseness control going from skin tight to more loose garments, transfer design from smaller models to bigger, design adaptation from the A pose, which is standard pose, to some other typical poses human bodies take. And finally, material stretch, where we mitigate excessive stretching when we do the design adaptation. Design expressivity, these are some examples of dresses which we made. These are partly parametric and partly done through the UI, and also highlighting the design transfer from medium bodies to extra large bodies. So the kind of one more question which is asked is whether this actually follow the prescribed ease in the physical fit, and the answer is it follows the trend of the prescribed ease when we measure the area between the body and the garment. The baselines compared to so when we compare our method to prior work, we start with this first informal mapping, which is simply 2D flattening from 3D, and we can see that some areas are expected to be problematic, which is highlighted in red, while the anisotropic baseline, which is the prior work, they actually solve this stretching problem. However, they do not have a control of ease, which is a contribution of our method. And when we compare cutting, which is fairly, so this is a bit unfair experimenting way. It's more to highlight that separating ease control from cutting has its benefits, but it can be taken because the prior work actually takes the 3D asset and does the complete cutting themselves, although the resulting cuts tend to be fairly irregular compared to our dress where we have two components. When we compare on a more realistic scenario for manufacturing of real pants, we did two pairs of pants, and this is one example on the tested subject. We also tested it on some other shapes, for example, horse. This is also parametric, so we managed to change from, let's say, regular size horse to a small horse, and the same effect as before. Key limitations is that we need to include darts. Darts are definitely one part which we're missing, so we need to add more cuts to be able to accommodate more complex shapes. Also, the garments which deviate a lot from the body are more challenging to design, and also there's perhaps maybe a lot of practical issues, although we didn't observe many in practice, which doesn't mean that they're not there. So this is a first-class design variable we introduce. We do not need to use simulations or resimulate for each of the results, and it's fairly fast. Thank you.
It's very nice presentation. Any question from the audience? I have a question. You showed that you can nicely transform your settings to another body shape, but they seem to me both very simple meshes and parametric reference models. What about a customer who wants to try on a garment on his own body scan? Do you see it possible?
So first, to fit such a simple parametric model to the scan, depending on the quality of the scan, this would be easy, fairly easy. But if, of course, we have a partial scan, then that's a completely different engineering problem. But the scanning part starts with, we assume that we start with a nice parametric model, yes.
Okay, so you don't have any requirement about having the same topology in the two meshes.
We require that once we enter our pipelines. If we manage to transform the input, whatever it is, whether it's a 3D scan to a nice input to our scan, so if we are able to do the reconstruction, let's say, then we can do the whole pipeline. But we require that we have the nice meshes.
Okay. More questions? So you showed also that there is some, you take into account the time of textile that you are using. Did you do any experiment on that so far?
So regarding the textile itself, our model is relatively simple. So what we is the how much can it stretch, how much can it tolerate a stretch, which you can model some part of the material properties, but the materials are very complex. So for material properties and other like enforcing, I think we would have to go to the simulation side because without the simulations, maybe this could be done as a post-processing step. But once the simulations enter the story, the whole optimization is much more complex, and I think we'll lose this.
Do you make any preliminary experiment with a tailor? What did they say?
Yes, so once the first time I came to them, they were puzzled, like to be fair. But over time, I worked with them so that they're part of the team, and we managed to get some kind of like a trade-off. So these are not yet production ready swing patterns, but they serve a different purpose. Maybe these swing patterns are not the core part of like the output, and pattern makers wouldn't appreciate it. But we work together to so with the line terms that we introduced later, we were motivated by this.
Okay, thank you.
So when you have the texture garments, like how do these seam lines come together? Like it's possible with the textures.
Actually, this is another paper we published, and actually it's a combination with some other things, but it is it's a separate optimization. We can take a texture and we can classify it into a type of texture that we have. For example, the stripes is one type of texture. Once we know the type, we know the constraints that need to be satisfied. What we use in our paper is the genetic algorithm, but I think if you only focus on the texture, it can be made simpler. So I think I'm not sure now, but I think you can solve this. I would say fairly simple, but I think it's possible not to use genetic algorithms.
No question? Last one.
Thank you so much for the nice presentation. I have a question regarding the way you model the garment, the fact that you explicitly penalize the shear, which is a bit counterintuitive in some sense because garments can shear. I mean, this is one of the degrees of freedom the garment has in relation of the orientation of the fiber. I thought you haven't considered about because if you cut a piece of cloth, right,
basically it's an extensible direction of the fiber, but it can share this now, right? So I think maybe as a diffusion work, you should consider also the direction of the fibers, possibility of sharing, which is one of the degrees of freedom of cloth in real life.
Definitely. So there are multiple answers to kind of shear problem. One is that you mentioned that of course the carbon will shear. What we want to retain are the directions. We have define the directions at the beginning of the organization, and we don't want these directions to change. So we don't want to get from something orthogonal to something skewed, then we do not optimize the correct direction. That's the main reason why we want to randomize it. But another problem with shear is that another problem with shear is that so it's actually fighting the other term, which is why it's good as a regularization. But if you put it formally, I think that the two terms fight each other. So in one sense that is good because you get the effect that you want, you get the regularization effect. But it is a bit contradictory to me that it works. So it is a good question, yeah.
Okay, thank you very much. For the next presentation, we welcome Sasinas alias Anita. She's going to present the logic triangulation-based sampling approach for the Voronoi diagram of spheres. Good afternoon, one and all. Myself Shachinas alias Harita. I'm from Advanced Geometric Computing Lab of IIT Madras. And I'm here to present my paper Delaunay triangulation-based sampling approach for the Voronoi diagram of spheres. This is the outline of my presentation. To begin with, I'd like to briefly discuss about the Voronoi diagram. So a Voronoi diagram partitions the space into multiple regions so that you can see that any point inside the Voronoi space, Voronoi cell, it will be closer to the object. That is here, if you consider, you can see that the point is the object here. So if you consider any point inside this Voronoi cell, it will be closer to this point. And the boundary of this Voronoi cell, you can see that it is a Voronoi edge. And when multiple Voronoi edges intersect, it creates a Voronoi vertex. So as we move from points to circle, you can see that the Voronoi edges, it will be changing from straight lines to the hyperbola. So here you can see if it is of equal radius, it will be straight line itself. If it is of different radius, it will be changing. So in 2D, we have Voronoi edges as well as the Voronoi vertices. As we move from 2D to 3D, you can see that we have Voronoi face, Voronoi edges as well as Voronoi vertices. So this is a Voronoi cell, and you can see 6 spheres here, and there is another sphere inside this Voronoi cell. Let me introduce briefly about the Delaunay triangulation as well, which we are using for the sampling-based approach. So a Delaunay triangulation, it is the dual of the Voronoi diagram. So two objects will be connected with a Delaunay edge only if there is a common Voronoi edge between them. So here you can see that if you consider these 2 point objects, there is a Voronoi edge between these two. And you can see that you're using the Delaunay triangulation. This will be connected only to the neighboring objects. It won't be connecting the faraway objects. It will be connecting only to the neighboring objects, which will be giving you the information about the neighbors in the input. So we are using Delaunay triangulation to identify neighboring spheres through adaptive sampling in our work. So there are wide variety of applications of PD, especially in the case of spheres. We can use it for molecular modeling, structural biology, shape analysis, and geometric modeling. These are few to mention. So I would also like to introduce about the general and non-general position inputs. I am using an example of a circle here. This is a 2D example. So here we are having 3 circles. So if you are having a circle tangential to these 3 circles, you can see that its center point will be the Voronoi vertex here. But if you use considering a non-general position, you can see that the tangential circle, it will be tangential to more than 3 input objects. Okay, so here you can see that there are 4 circles here, and this tangential circle, it is tangential to more than 3 input circles, and so that will be the center will be the Voronoi vertex as well. In 3D also, we are getting a lot of non-general as well as general position configuration when we are considering large number of input. The existing approaches which are existing for the video spheres, we can broadly classify it into 2 categories. First one is bisector and trisector based approaches, and the lower envelope based approaches. The main complexity with both these approaches are, you can see that both these are computational demanding. And also most of these works which are existing, in most of the cases, they're computing the Voronoi vertices, but they need separate edge topology and face topology for constructing the complete Voronoi diagram. And also in most of the cases, isolated edges, non-general configurations, and intersecting configuration remain difficult for handling. So if you consider this particular example, here you can see that we have 2 input spheres. There's not input spheres, input circles. And here there are multiple bisector segments, but only one of these bisector segments is actually contributing to the BD. Here this green bisector segment is actually contributing to the BD. The other one is not contributing to the BD. And if you further look at the Voronoi diagram, you can see that in this bisector segment itself, only a small portion of the bisector segment, you can see it in the green color here, only a small portion of the bisector segment that is actually contributing to the Voronoi diagram. So our main question was, can we compute BD topology without explicitly constructing bisectors, trisectors, or normal envelopes? So we wanted to compute the local topology of these Voronoi segments. And here you can see that if you are getting these Voronoi vertices detailed, it is possible for us to locally compute the Voronoi segments. So that was the main motivation behind our work. So we are using a touching ball approach for computing the same. So if you are considering the sphere bisector, you can see that it is hyperboloid of torsions. And again, ours is a sampling based approach. Why do we need a sampling approach? So this is another example of Voronoi diagram of a set of circles. If you consider this big circle and this small circle, you can see that there is no interaction between these 2 circles, and there is no Voronoi edge between these 2. So we did not have any computation between these 2 for identifying the Voronoi diagram of this set of circles. So in order to ensure that we are only processing the neighboring circles, we are using the help of Delaunay triangulation to find the neighbors. So if here we are taking the center of Delaunay triangulation of center of circles, you can see that using the Delaunay triangulation, we will be getting the neighboring information. But when we took the Delaunay triangulation of center of circles, we identified that that is not sufficient always. So we came up with another strategy for solving that is adaptive sampling. So these are the key contributions of our work. A touching ball framework for computing the video of spheres without explicit bisector or trisector construction, a DT-based adaptive sampling strategy for identifying neighboring spheres and generating the relevant triplets, and a directed freeze data structure. We have introduced a dynamic data structure, directed data structure for encoding the Voronoi segment growth as well as the topology. And our algorithm also handles the isolated edges, edge humps, and several non-general and intersecting sphere configurations. Our work is mainly based on the touching ball approach.
So a touching ball is tangent to 2 or more input spheres. A 3-touch ball, it is tangent to 3 spheres. So here you can see the 3-touch ball TTP, IJK. And if 1-touch ball is tangent to 4 spheres. So here we can see FTB, IJKM. And we can see that in empty FTB, it represents the Voronoi vertex and it is also called as a junction ball. And Voronoi balls, all the empty touching balls are located on the Voronoi diagram as well. And their centers will be tracing the Voronoi segment. So Voronoi segments, it is defined using the touching ball events or touching ball configurations. So it is computed locally, as I have mentioned, I'm focusing on locally tracing the Voronoi segments. So here you can see that we have a 3-touch ball. This 3-touch ball, its center will be acting as the arm minimum radius will be minimum there, and we have FTB center which will be acting as the arm max. So the segment will be growing from arm to arm max, and the intermediate Voronoi poles are also shown using the pink color here. So you can see the black segment growing from arm into arm max. Similarly, there is a blue segment going from arm into arm max. So we are splitting it and finding the multiple Voronoi segments and finally tracing the Voronoi edge. And in some cases, you can see that the TTB will be no longer empty. If the TTB is not empty, you can see that there will be some FTB which will be acting as the arm for tracing the corresponding Voronoi edge if it exists. So here, both arm as well as arm max, both these are FTB itself. For representing this Voronoi segment and the direction of growth of the Voronoi segment, we have introduced the directed phases. A DF is constructed using the foot points of the touching ball. So here, a directed phase is represented using a triangle here. So this is represented using the foot point of all these 3 spheres, SI, SJ, and SK. That is the location at which this touching ball is tangential to these foot spheres. And again, it shows the direction of growth of this Voronoi segment that is represented using this arrow. So you can see that we have DF, IJK as well as in the reverse direction, we can call it as DF, AJI. Our assumption is that the Voronoi segment always goes towards the right side of the directed phase. And in the case of non-general configuration, the change is that you can see that a particular touching ball, it will be representing multiple directed phases because we have more number of combinations coming up there. So this is the core idea. We are completing the topology first and geometry later. So we have the set of input spheres, and initially we are performing the DT-based adaptive sampling for identifying the neighbors. Once the neighbors are identified, the triplet identification will be done, and after identifying the triplets, TTBs will be generated. And if the TTB is empty, in that case, the directed phase will be introduced. And it is using the directed phases that we decide whether an FTB exists or not. If the two TTB directed phases are having a common edge, then an FTB will be created. And after FTB generation, when we are processing the FTB, again, emptiness of FTB is also ensured using the systems of directed phase itself. Once this FTB is identified to be empty, its center will be acting as a Voronoi vertex. And once we get the Voronoi vertices and the local topology of Armina artworks, once we identify all these details, we will be creating the geometry, that is Voronoi edges as well as the Voronoi spaces will be created. So we are using a DT-based adaptive sampling for the triplet identification. So here, as you can see, initially we are identifying the DT of the center. We are using the DT of centers for identifying the neighbors. But as we have discussed and which I will be discussing later, the DT of centers are not sufficient for identifying the exact neighbor. So here in this method, after finding the DT of centers, we are finding the intersection of this tetrahedron onto the sphere. You can see that here. Tetrahedron onto the sphere. In that triangular patch, we are finding the samples, and after finding the samples, all these samples will be collected, grouped together, and the DT of the samples will be found. This will be giving us the exact input information. So this is a 2D depiction of how the sampling is done in 2D. So why adaptive sampling is needed, that we can identify from this diagram. So here you can see that if you consider the DT of senders, this sphere SI and SJ, these are closer, but if you are just using the DT of senders, SI and SJ are not identified as neighbors. But once you are using sampling, you can see that SA and there is an edge connecting the SA and SJ, and we can identify that these two are neighbors, exact neighbors. So its corresponding 2D depiction is represented here. So if any missing neighbor relations are there, in that case you can see that we may not get the exact Voronoi diagram. So that is ensured using the adaptive sampling approach. During the TTB processing, our main idea is for identifying which are the empty TTBs, and after finding the empty TTBs, we have to introduce the directed phases, and after introducing the directed phase, we have to check for the possibility of creating the FTBs. So here, for checking the emptiness of a TTB, we are not going to check with all the input spheres, and instead of that, we are going to only use the parametrically closed spheres here. So here, if you are considering the S2, S4 and S3. The directed phase S2 and S4, S3. So this is actually represents a TTB here. So if for checking its emptiness, we'll be checking only parametric closed entities like S1, S5. That is this, you can see that it is sharing this particular edge here. Similarly, there will be spheres which is connecting this edge as well as this edge. So we are not going to consider all the input spheres, only parametrically closed spheres will be checked for identifying the emptiness. So as we have seen, once we have identified the directed phases, after identifying the directed phase, FTBs will be created. And all these TTBs and FTBs in our algorithm, we are inserting into the same list in the increasing order of radius, and we are processing it. So when it is time for processing an FTB, what is being done is, first of all, we have to check whether it is empty or not. For checking its emptiness, we are going to check whether the corresponding DFs are present or not. If two DFs are available, or if two or more directed phases are available, then we can say that FTB and FTB is empty. If it is empty, its center point will be the junction. It will be a junction ball, and its center point will be a Voronoi vertex. So here, if it is an FTFB and empty FTB, Voronoi vertex is created. And if it is an empty FTP, one more thing that we have to do is, if there are any missing directed phases, those missing directed phases will be reintroduced so that we are not missing any other FTPs for creation, which is possible if it is already existing. So we will be introducing the missing DFs and create new FTPs if any. So this is the overview of our method. So this is a working example where two directed phases are available. As I said to you, we have three cases: 2 DF case, 3 DF case, and all the 4 DFs are available. So, initially we are computing the TTBs and we are processing the TTB. We found that this S1, S2, S3 TTB 1, 2, 3 is empty, and the directed phase is generated and it is inserted there. Similarly, DF 2, 3, 4 is also included. And then we are finding that there is a common edge between these two directed phases. So when there is a common edge, if the FTB is created, after creating the FTB, it is also inserted into the same list. And again, the remaining TTBs are processed. That is, TTB 421 is processed, and then TTB 431 is processed. But you can see that those two are not empty, so it will not be considered further. And then afterwards, when the turn of this FTB comes, it is processed. After processing the FTB, it is identified as a Voronoi vertex. And when it is identified as a Voronoi vertex, as we have already discussed, you can see that the missing directed phases, that is, directed phase 431 was not included. Directed phase 431 is again introduced here, and directed phase 421 is also introduced here. So after introducing both these, again the possibility of creating the FTB is checked, but since it is already FTB 1, 2, 3, 4 again, it is not introduced again. It won't be introduced again. So here this is the basic working example of our algorithm. And for the geometric realization, as I said, we have the local topology information, we have the Rmin details as well as the Rmax details. So we are going to locally construct the Voronoi segments. So from Rmin to Rmax, there is a radius tube that will be done, which will be providing with the Voronoi segment. And Voronoi faces are constructed locally after the edge topology is known. And this is a 2D analogy of the touching ball method. So here, instead of the directed phase, we can call it this is a directed edge. You can see that the Voronoi segment can go to both sides, that is towards the right side of the directed edge. So here, there are between C3 and C2, a segment is going towards the right side, and between C2 and C1, a segment is going towards the right side. But this antipodal disk, that is the disk between C3 and C1, it is not empty because it is not empty. It was not introduced. But later, during the processing of this particular TTD, we call it as three-test disk. During the processing of the three-test disk, this C3, C1, it was reintroduced, like we were reintroducing the directed phase, and then the corresponding segment was identified. Okay, the same approach we are using in 3D, that is, we are identifying the TTB, then we are representing it using the directed phase, and then FTB is created, and the Voronoi vertices are identified. That is the procedure that is being used. This is the final example of non-Voronoi diagram. And we are also handling isolated edges and edge hubs. In the case of isolated edges, if two TTBs of same indexes are coming, it will be identified as an isolated edge and it will be processed. It doesn't require any special conditioning. And also in the case of edge hubs, you can see that edge hub can split the closed trisector into multiple Voronoi segments, and there will be multiple FTBs with the same indices. But since we are using the food points for identifying the FTBs and TTBs, it will be handled without any special conditioning. It will be handled by the algorithm. These are some examples of results. And we have also handled all the complex configurations adapted from the key method. And this is a runtime comparison of our method with two existing parallel approaches. Ours is a sequential algorithm, one with Mugnan et al. And Voronoi et al. In our approach, you can see that we are computing the Voronoi edges, Voronoi phases, the complete Voronoi diagram is constructed. But in the case of Voronoi et al., they are identifying the Voronoi vertices, but not the edge and phases. And in the case of Mugnan et al., you can see that even though our algorithm is sequential, it is on par with the Mugnan et al. Almost up to 4,000 spheres. And for showing the scalability that we have tested on large number of spheres also, you can see that this is the graph representing the scalability. And for showing the computational complexity of algorithm, you can see that the number of generated samples as well as the number of TTBs, it is almost linear in the, you can see from this graph. So in the existing approaches, you can see that if you are comparing the computational complexity, bisector-based methods compute bisected surfaces at trisector intersections. One of the major problems with these iterative methods are that is it often suffers from convergence into an invalid bisector. And again, they have to recompute it, which is going to have some additional computer overhead. And in our proposed method, we are defining the local touching ball configurations, and it is represented using the directed phases, which will be addressing the local topology, and it avoids global bisector processing and unnecessary combinatorial expression. The limitation of work is currently it is sequential, and again, if the spheres are of equal radius and in the same line, in that case, it is not addressed. And also, containment cases are not addressed in our case. So, the future work is parallel implementation and extension to the sphere containment cases. To conclude, we have proposed a DT-based adaptive sampling and touching wall framework for video spheres. And this avoids explicit bisector trisector intersection during topology construction. And also we have introduced a directed phase to propagate the Voronoi segment connectivity. And our algorithm handles isolated edges, edge humps, and several non-general and intersecting configurations. I'd like to acknowledge my professor, Professor Ramanathan Muthuganapathy. I'd like to extend my deep gratitude to him and also the reviewers and committee of SMI 2026 and the members of the AGCL lab and my co-authors. Thank you.
Very much for your nice talk. Questions? Okay, I can start. I've worked a very little bit on proteins, so I think the application that you showed in the beginning for molecules and proteins is very nice. In that case, you might have to manage handle the case of intersecting spheres, maybe. So, do you plan to tackle this open problem that you mentioned in the end? Are you going to do something with that, and you have already some ideas?
Yeah, containment cases are not addressed. We are planning to address it. We haven't formulated it completely, but we are still trying to address it.
Okay. More questions? So about I think the core contribution is in the speed up of your method to compute the Voronoi diagram in 3D. So do you think the parallel computation and maybe, I don't know, you showed that in your results, when the number of spheres increase a lot, the time needed by your algorithm is quite comparable with another previous work. So do you think that the parallel computation will decrease a lot the computation time, and I think it is quite easily parallelizable because it's a local approach. Is it correct?
Yeah, we are expecting that it will be reducing a lot. Already we are, as I have shown here, it is on par with the Mugdhan approach, Mugdhan et al.'s approach to some extent up to 4,000 spheres. But later we have found that there is a difference in the time. So we are sure that for large number of spheres, if we are parallelizing it, it will be reducing the total amount of time. And our major contribution was on reducing the computational complexity. We were focusing on the computational complexity rather than reducing the time as of now. But if you're parallelizing it automatically, we are expecting that it will be reducing the time as well.
And what about memory consumption? Do you think you can handle a lot of spheres?
I think having resources definitely will be able to.
No, very nice. I think it's a really useful contribution. Thanks a lot.
Thank you. Thank you.
Okay, so we move to the last presentation. The next paper is adaptive surface reconstruction method based on growing neural gas. And the presenter is, I think, Xinhua.
Okay. Good afternoon, everyone. My name is Qin Qinwang from Beihang University. Today, I am very pleased to present our work entitled an additive surface reconstruction method based on
Hello, everybody. Welcome back. So this is a CC3 mesh processing, and we have 4 excellent and interesting papers from SPA. And the first paper is local demo, building scale 3D denoting tabulation on a single GPU. The presenter is Wu Gao from the University of Science and Technology of China. Thank you.
Thanks for introduction. Good afternoon, everyone. I'm Wu Gao. Today, I will present our work, local demo Boolean scale 3D dynamic calculation on a single GPU. This is a joint work with my advice. Three-dimensional dynamic calculation is a fundamental structure in geometry computing. It is widely used in visualization, finite element methods, volumetric meshing, and various simulation pipelines. As acquisition and simulation data continue to grow, we increasingly need to handle one set with hundreds of components or even millions of samples. This makes a high level of GPU direct kernel element and important. For large one size, a practical GPU parallel strategy for constructing the direct calculation is to decompose the problem into many local computations. Instead of reasoning about the whole calculation locally, we let each one process its own neighborhood in parallel. This gives us a single and scalable view of the computation. Local triangulation structures are built independently and then combined into the global dynamic triangulation. A natural local structure for this one-wise strategy is the dynamic one ring. For each point, we can construct this dynamic one ring by taking the union of all one rings. We recover the full dynamic triangulation. Equivalently, this process can be done in the Dor space, that is the Dor monoisil of same point. For 3D dynamic calculation of the GPU, Cao et al. Proposed an early method based on batch inversion and parallel bilateral free flipping. However, their method first built a near dynamic calculation on the GPU and then transfers it back to the CPU. Final prepare using adaptive star speed. Therefore, it is not a fully GPU parallel implementation. Another related method is specialist Voronoi by VIO, which constructs Voronoi cells through half-space intersection with nearby points. To reduce the complexity of the naive Voronoi cell intersection method, they introduce the release of security, which defines a region where points are chosen for half-space intersection with the kernel Voronoi cell. However, when the release of security cannot be reached, which would happen for some in their method, the resulting Voronoi diagram is likely to be incomplete and cannot reliably produce the weighted dynamic mesh. A more relevant comparison is our own work from last SPM, PDT. PDT is also based on half-space intersection, but it includes locality within the local dynamic lemma. It directly outputs a direct calculable mesh, and the construction is fully GPU parallel. Overall, PDT achieves about 3 times speed up over the scale out. In the half-space intersection method, all the technical in one share the same central vertex. Therefore, it is sufficient to store only the boundary of each local Y-ring. We record first the indices of the different points, then the local triangle connectivity among them. While this works for half-space intersection, it is quite memory heavy. For this rather small neighborhood, it takes a total memory of 78 bits. As runtime performance on the GPU is limited by memory bandwidth, reducing the size of this local structure is a key point for optimization. So the question is, are we avoid exploring the full-time regulation? Let's begin with the full dynamic winding of a target point A. Note that when we look at the set of binaries for all the points in the point set, each tetrahedron will appear 4 times. In other words, each tetrahedron will appear in the binaries of all 4 of its vertices. As such, we can discard a tetrahedron where point A is the leftmost or rightmost vertex in X order. All the remaining tetrahedral cross the plan X equals XA. We call this subset the local equal of A, and the plan the local equal plan. For each stellar tetrahedron, we solve its 4 vertices by X coordinates. Then this tetrahedron will be found in the local equal of the middle vertices. So every tetrahedron in the global mesh will appear in some local. And the union of all local equals the complete triangulation. We found that the local equal can be represented much more compactly than a full binary mesh. Instead of explicitly storing the triangulation, we can instead store an ordered list of points. And that is sufficient to infer the triangulation at runtime. We will use the set bit of the indices to distinguish points on either side of the local plan. From this ordered signed list, the whole triangles can be reconstructed implicitly. Take the first triangle as an example. We use 2 consecutive points in the list and find the nearest previous point with the opposite sign. In this way, each triangle can be recovered from the list without explicitly storing the triangulation. The next question is how to build the local equal efficiently. A standard composite intersection algorithm keeps a closed convex polynomial by the bisector plan. However, in our case, the local equal is only a stripped subset of the one ring, and its store becomes a polygon in R3. This makes it difficult to adapt House's intersection for our local equal. We propose to construct the local equal with a troublesome method. The idea is to start from an initial direct tetrahedron on the wall. We choose the direct tetrahedron intersected by a target ring of the plan as the initial tetrahedron. And then walk to its adjacent tetrahedron along the local equal plan. On the traversal from space where it started, the loop is closed, and the local equal for this vertex has been completed. We can see that our local equal allows significantly reduce memory traffic. By replacing explicit triangle operation based on binary storage with compact local equals, our method provides repeated reads and updates of mesh conductivity. Furthermore, the traversal algorithm is local and read-only, leading to much reduced global memory access and better GPU cache behavior. Together, these 2 designs reduce global memory traffic by about 10 times. Our implementation follows similar organization techniques as done in PDT. We use the bucket data structure to support severe search in order to find nearby candidate pods. Since the complexity of the local equal construction varies from point to point, especially those scanning tests where the point distribution is sparse. For example, near the boundary of the convex hull, the runtime complexity of our traversal algorithm can increase significantly. Therefore, also adopt a 2-stage kernel design to improve workload balance across GPU suites. Now let's check the results. We first evaluate our method on 3 nearly significance: white noise, turbulent rate, and blue noise. Compared to PDT, we can see our method consistently demonstrates higher efficiency for coordinate distributions. While our method is being designed for uniform distribution, we also test non-uniform distributions generated with different density functions. The number in bracket are acceleration compared to PDT. We can see that our method remains stable under these non-uniform settings. For the more challenging Laplace distribution, our method is more than 4 times faster than PDT. Here we benchmark our method against state-of-the-art CPU and GPU baselines on uniformly distributed one sets. Across the tested input sets, our method achieves the lowest runtime. For 10 million points, it finishes in about 0.4 seconds, which is more than 2 times faster than the state-of-the-art and much faster than parallel CPU implementations. Here we report the normalized runtime measured as the average time of million points. For extremely large inputs, the output triangulation may not fit entirely in GPU memory, so we switch to batch mode and process about 1 million points at a time. The vocal lines on the right indicate this switch to batch processing. Our experiments show that to produce 3 billion tests, our method takes only 20 seconds, while Gmash requires 53 seconds for the same task on their 64-thread CPU. We demonstrate our method on restricted dynamic triangulation. Our method does not yet support constraints of any form, including boundary edges or weights. Hence, we currently cannot recover a triangle mesh as the boundary of the output generate triangle mesh. As a remedy, in this application, we sample points inside and around a bounded surface, then compute the unconstrained 3D dynamic triangulation. Finally, we remove tetrahedral that lie completely outside the surface. Our method can be used for efficient mesh optimization, such as Floyd's iteration. Here, to generate CVT, the sample points move iteratively during optimization, and the underlying dynamic triangulation has to be updated many times. Our method makes its repeated triangulation steps highly efficient on the GPU, along with the one optimization step. So why do we call our method local default? As many of us know that the name default, which has existed in the literature for quite many years. Indeed, our local default is related to default, but only in two sense. First and foremost, our method is not based on the original divide and conquer default algorithm. We picked this name because of simple geometric resemblance. Both involve simplicities intersecting a plan structure. In our case, the structure is local to each port and built independently on the GPU. To conclude, we propose the local default which provides a compact encoding of the 3D dynamic triangulation as an ordered portraits of work. We developed an experimental method to construct each local default by traversing adjacent tetrahedron, drastically reducing memory footprint and traffic. As a result, our method achieves more than 2 times speed up for state-of-the-art and scales with billion more dynamic triangulation on a single convertible GPU. For future work, we plan to optimize the algorithm for non-uniform distributions and extend it to support constraint triangulation. Thanks for listening.
Okay. For your last presentation work. So let's come with a question. Question.
Yeah.
So, just a quick question. I know that lots of people need the volume diagram instead. So Chile depends on for etc. Because you can actually do the delivery. Have you thought about transforming what you found on the GPU into a volume diagram, meaning to visualize your construction so that you can output a volume mesh instead? And would that be faster than something like Volume that's limited to CPU?
Do you mean that translate the direct migration to honor measure?
Exactly.
That it's straightforward. I think it's I don't know how to say. It's easy to transform the direct calculation to one mesh. Since one one is the mass layer center of the generator.
Yeah, but you need to compute this if you have a billion block. That's not trivial matter. So my question is, if you do your local involved thing, and then you transform into a volume mesh, is it faster than doing directly vol plus plus type of algorithm?
Yeah. The 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 compare the word meshes or learning is the straightforward for one mesh. We compare it.
Okay. Thanks.
Any other questions, audience? I have a question for. So when we use these two future, one of the surface constraint, the second is non-uniform. But I see some result non-uniform distribution for the input function. So yes, what do you mean here? But it looks like you can working on some density-wise changing of the function.
Non-uniform is still I think it's still for some non-uniform we can wait as well, but for some or non-uniform it's really we can also compare for the CPU manual.
So what's the challenge for the non-uniform? Do you have any thoughts here?
Maybe without more graphics, it's very heavy to use the exact graphics on the GPU.
Okay, thank you. Any other questions from the audience? If not, please set speaker again. The second paper is weakly supervised learning for 3D mesh segmentation while the pixel level labeling. And the presenter is Wei Ying Ma from the City University of Hong Kong.
Thank you, Chairman. And also thanks so much for all the organizers of the conference. So let me know. I think that this time is joint work with everyone with, and also in collaboration with that PLL and so process. Actually, this work is mainly about 3D mesh segmentation. So it's mainly focused in that area. However, we apply deep learning techniques to achieve the final segmentation. I think normally the work should be presented by Dr. Wu, but who cannot be here today, so I will present everything here for today. I think for the following, I will briefly highlight what we have done, the main procedures, how to achieve the final segmentation results, and then briefly mentioning about the conclusions and also future work. So basically, the main motivation actually is the following. If we do 3D segmentation using deep learning techniques, usually in order to do the training, we need to label the input dimensions extensively with all the with many samples. In order to do that, actually, it's very time consuming and tedious. So the main idea is that we develop a technique where we apply a simple sketch-wise labeling on a 2D image for the 3D mesh. And then goes through a further training learning process. And finally, we could achieve 3D mesh segmentation. So the final results actually could be used in two directions. So first of all, the final results we push here can be applied as for labeling of meshes for different learning applications. Second, actually, the results can also directly used for as segmentation results. So basically, it can be used for our learning process. It can also be directly used for segmentation. So here is the ideas what we're talking about. Basically, give an input mesh. So basically, it's triangle mesh. We produce some views from the 3D mesh. And then we do a simple labeling going through a simple sketch somewhere here and there with the most important areas. And after that, so using such a simple the sparse labeling, and then finally goes to a further actual tool learning process, we have achieved the final segmentation results. This is hopefully it can be used as segmentation results, and also we could be used as 3D labeling for other applications. So that's the main motivation for what we're doing. So usually from the initial labeling, actually, usually we produce about 2 to 5%. Actually, depends on how many units we use. So we are 2 to 5% for triangles that's labeled correctly as what we want. So this percentage depends on how many units that we use. So in that case, the main motivation is that we use a simple 2D labeling to achieve complete 3D segmentation. I think that's what we very much so useful simple 2D labeling and that useful the further transformation and finally we will achieve the segmentation of an input mesh of a single input mesh. Here you see an overview of the whole procedure. Basically, it's performed in three different phases or steps. The first step is mainly about the 2D labeling. So basically, from some selected views, and then we sketch the main areas we want. And after that, in the second phase, we call instance specific label propagation. The main reason is that after initial labeling, actually the area of the final meshes that has been confirmed may not be that much, like we mentioned, 2 to 5% or sometimes 10%, may not be that much. So we perform some kind of it's like region moving. So it's for mesh, further propagation such that we can achieve the segmentation. After the second phase, although the results look already normalized, however, if you look carefully at the partition boundaries, may still be not that smooth. And then we further apply another further learning process, and where we can improve the boundary, make it further smoother. So that's the main steps we follow. These 3 steps or more phases. I think the main contribution is matter first of all. The main idea basically, if you do 3D labeling, it's very complicated, very difficult. However, here, if you go into 2D labeling, it's very easy. Secondly, for the interactive specific propagation, mesh propagation, actually we apply the existing procedure. We apply that learning approach for here so that we could achieve what we want for the segmentation. And finally, for smooth actually is also we apply another procedure, it's also learning approach, and then you can further improve the false boundary so that it can be smoother and smoother. So that's the main work in preventing work. So for phase 1, step 1, we're talking about 2D labeling. I think what we have done is so based on input mesh, the architecture of input mesh. First of all, we decide our main architecture, and then from that architecture, we find out best view from I think about 50 directions. Based on that main view, and then we can further produce easier 3 view or 6 view for the 2D labeling. So which means that for 2D labeling, can use easier single view or 3 view or more than 3 views. Most of them use 1, 3, or 6 views. After that, of course, from the 2D image labeling, signal labeling, we need to further map the 3D meshes. That's a simple procedure. So it's a mapping process. So that's the main work in phase 1. Here you see some of the examples, 2 examples from 2 data sets from the literature. And the first one is here. You see for this case, we picked up 6 views, and where you see for each view, what sketch we put there for the later segmentation. The second example is a whole body model. You also see 6 views will be picked up. Actually, these are optimized activity. Actually, it is from the main view, and then you can further produce 6 views that's standard views. So for the first view, it's optimized view. So in any case, these 2 examples, we see how do we produce 6 views and where do we mark the sketch for labeling. So the main observation here is that after we map the stable sketch to 3D meshes, of course, we can only confirm balanced mono triangles for segmentation. That's really, of course, is not enough. So what we need to do to achieve finally for the complete input mesh, we want to partition into really regions, meaningful regions. For that reason, and that we go for the second phase, and that we call instance specific TCN, so vector learning approach. For this case, actually, it works a single mesh by single mesh. The main idea is that from input mesh, And that based on the 2D labeling, we apply an iterative process. So from initial only a few percent of the triangles goes through the learning process, it will go finally you can achieve the total partition of the whole information. So it's an iterative process. For each of the process, it's a deep learning approach. So that's for phase four. However, in this case, is very specific, which means that actually for the learning process of training, we only apply the results what we have for a single example, for a single object. We do not apply many other model training. And we use actually it's a very simple graph. The graph is a very simple graph. Basically, this graph collects the main information we need, for example, what the neighborhood information we need, like pressure information is a var, distance faces, with each information, and that goes through the training process. Then you can find the activity information. Exactly for this training process, we use in total 140 parameters of variables for the training process. This is the parameters back on example, like orientation, the position information. I think it's the phase wise. So like position information, relevant application, position, and also the start hardware information like nearby and also altogether there are 140 parameters we use during the training process. The main training and loss function we optimize the exercise mainly. First of all, starts for it. So from a few confirmation, gradually we achieve more and more close to the triangles segmentation. Second, of course, we infer confidence labels. Usually, if we, of course, we gather the ranking of the confidence of the manager, the hiring manager. Finally, we reinforce the temperature where smoothness later one potential. Here you see I said two examples for the illustration wow. For this case, let's compare the amount of factories SVP from the yeah, is now maximum second resolution specific training. For this case, actually we also differentiate using the first data sets. The first data sets error one. It means that in this case we only use a single view for the 2D labeling. And whereas this case is that there are three views in the line six views. And also another example of student age. What you see is that after the second phase, you see we could already achieve and a higher percentage of phases which are partitioned already well compared with the school partition. Actually, the initial data is getting there, but we know the answers from initial data. So that's after the second phase. However, the problem here is that after the second phase, actually, if you look carefully between the regions, partition the regions, the boundary may not be smooth movements. So what we're doing actually, we apply a further training process. We are actually in this phase, we produce multiple models. And after this phase, and also after basically it depends on the confidence level training was. After this phase, we further, of course, have from the battery, of course, we use the most reliable phases and finally we saw similar type what has for finding environments in long term for good boundary results. I think this is not also finding slides. So here we come, we witness several items of learning. So basically, it means that we only use minimum information very good efficient and correct for the final whole training process. Here you see three examples. You see which this also our maximum which is this certain class from the larger smooth itself. See however, you say that the main purpose for maximum is not mean that we can achieve always better than others. It's not like that. It's merely to achieve something which is very simple, going through the 2D leveling. Otherwise, it's very difficult to achieve. So final conclusion. So in the other case, we propose an efficient for efficient 3D mesh segmentation. However, going through very simple 2D leveling or 2D mounting. Basically, if you compare if you typically it's operation, otherwise it's very tedious, but here is very convenient to use. Means also very low cost for labeling. Maybe just mention future work. Actually, first of all, for the second phase, actually we're talking about the instance of circuit training, where actually each time we will only do for a single model. You may imagine if we produce the apples of many others, that may also be the assembly. And secondly, for free improvements about the battery. Of course, we improve the battery already afterwards, make it as smooth as possible, but still, of course, there's a lot of space. I think that's all. Thank you. Yes,
Thank you for the speaker for the nice work. So, any questions from the audience?
Thank you for the last presentation. Maybe I missed, so I just wanted to ask in which phase of your pipeline the different views are put together?
Only is the first phase. So during the first phase, we can use single view or three view or multiple views user and six. Actually, the main purpose for that phase is for 2D labeling. After that, we map the form pixel map back to triangles.
Okay.
So right for the initial phase where we use views. Otherwise, only the
yeah, sure. And is it the human annotator who selects the views, the different views, or you choose automatically?
Actually, I should say automatically. It's manipulation input of the original model to manipulation. From that interpretation, we do an initial optimization. I think from the interpretation, we pick up the axis, we find the optimal view among, I think, about 50 samples. The main purpose is mainly for collecting view where we can cover most areas of the model. Based on that view, the all other studio systems are needed.
See, the very last question. Do you, in what you showed, the method is really good in locating real 3D segments, so volumetric features. Do you think you can train your method to locate also 2D patches that are unique, for instance?
I think that is impossible. Actually, my course we before earlier is working on the image processing. I'm valid for the work that because we manage work on CD technology, so we apply exactly what we need before for CD measuring management. Actually, there's some complications on as well. The first also about movie, for example, like a medical image segmentation. Yes.
Thank you very much.
Any other questions? I have a question. So we're network, and like what you see here, the the major contribution for this work is you can labeling on 2D, then you can 3D mesh. So I'm wondering, did you compare with some other existing 3D labeling? Like, do you have some numerical tables? I see some very nice.
Yeah. I second understand what you are asking. I think the main idea is that going through 2D labeling is very easy and simple. Although we did not produce that in comparison in that sense. However, again, if people are talking about deep learning techniques for 3D mesh processing, the labeling is very complicated. I say that's what's going to be
Another question is, do you think, because first I saw the title, I imagine you are labeling on some image from the natural image. Do you think you can working on these natural image pictures, which can, for that picture, 3D mesh?
I'm not sure that may be another area for model reconstruction from 2D image to 3D. For this work, the input is a 3D mesh. So we want to partition the mesh, 3D mesh, into regions to interest. So it's called 3D mesh segmentation. It's usually it's very useful for versus the area for category for segmentation. So the input is a 3D mesh for this case. The output is a segmented 3D mesh model.
Thank you. Any other questions?
I just want to learn the repeatability of your method. I say one person draw lines the image, so from 6 different views, and he again repeat. So he draw lines again. So the lines will be a little different tilted, let's say.
Yes.
What about the segmentation results?
Yes.
Is it different too?
Yeah, I agree. Usually for the deep learning techniques we apply, there would be some uncertainties usually. The results would be fuzzy. Sometimes may not be exactly like. Maybe it's a confidence level. I think for the analysis for this case, is based on our movement. It's based on 2D labeling, 2D marking from 2D images of our 3D model. So the results will be depends on where to be marked and how many times to be marked in your writing language.
You mark the same. So the segmentation results will be hidden different. I don't know how.
Actually, you're right. That's marking labeling is very important. Usually, we have to mark sometimes people make mistake about that area and should be following a region for each. So you are mistake about that way and that way marker behind somewhere in the middle. Or if some of features like that, just mark in the middle. But the other thing is the labeling process compared with 3D labeling is very easy. Only compared in that case.
Any other question? If no, let's thank the speaker team. Thank you. Yeah, I just want to check the third paper. Also, okay. And the third paper is accelerating cost of distance computation between triangle meshes while spatial locality. And the speaker is Wenbo Yang the Bayham University.
Hello everyone, my name is Liu Bo. I'm from Bayham University. We will our work on accelerating distance computation with geometric patterns. I will explain the problem, the method, the safety idea, and the experimental results. Let's start with the background. How do distance values was against geometric value between two shapes? In this figure, the outcome is a source mesh, and the lower surface is a tangent mesh. For each point on the source mesh, we found the shortest distance to the tangent mesh. Most of these local distances are not the final also. The horizontal distance is the largest local distance. In the figure, this is shown by the Minton value. This metric is important in mesh simplification, remission, and reconstruction. We need the largest total error, not only the average error. The problem is cost. If both matches have many triggers, exact competition in many nearest point queries. This is slow for large models and high precision settings. The baseline method uses branch and bound with cascading all bars. If a local is strong, it can draw many triggers and avoid many subdivisions. But there is still a key overhead in the subdivided stage. When a channel is subdivided, new channel vertices are created. For each channel vertex, the baseline starts a unit point query from the root of the target WH. This is called start query, and it doesn't use information from the parent vertex. Each child vertex goes back to the previous root and performs a globe transfer. The key observation is simple. A child vertex is usually close to its parent vertex, so the unit surface of the child is often related to the unit surface of the parent. If we ignore this relation, many globular shell cells become limited. This is a cause where we want to reduce. The core idea is to use spatial locality during subdivisions. First, subdivision creates a child vertex near a parent vertex. Second, the child inherits the parent's unit surface and initial gas. Third, we search for vibrating hole around this face. This gives a long distance value. Then we compare the long distance with the current global bound. If the local distance is small enough, the child vertex can be the out-of maximizer. Then we plot it and skip the global image query. If the local result is not enough, we fall back to the global image search. The method is not replacing exact search with an unsafe approximation. This slide shows where the acceleration is using the full branch on the appraisal. At the beginning, we build the AAB branch for the patch mesh. We also build the phase-time urgency matrix. This shows us which phases are very labels. During subdivision, we process the new vertices. For each new vertex, we get the unit surface information from its parent vertex. This is a hierarchical spatial interpretation. Then we run the one-click neighborhood search, which is related face and adjacent faces. This gives a local minimal distance called local. Next, double counting decides what to do. If the local is below the global bar, which gives a BVH query. Otherwise, we run the global BVH query and use the local and global bar. The story rule stays the same as the baseline. We update the bounds until the required terminal state is reached. Now I will explain why this method is safe. The local value search gives a distance value. This value may not always be the only distance, but it is still a value bound because it is a distance to a fixed bound function mesh. The planning rule uses this bound carefully. If the local is smaller than the current global bound, this point can be the maximum point of the hollow distance. So we can simply skip the global image query. If the local is not enough for planning, we fall back to the global image search. The global query gives the exact unit distance. This fallback keeps the same accuracy target as the baseline. With the speed up comes from skipping unnecessary previous queries. It doesn't come from changing the final item block. Now let's look at the experiments. The first experiment is general benchmark. We use 29 or 998 match pairs from the schematic datasets. The 20 matches are simplified ways of the sub matches. The pie chart shows the period of the hierarchical spatial installation. Can mean that the unit surface of the channel vertex is found by the inherited face or its local neighborhood. The result is strong. In 71.5% of the cases, the hit rate is at least 99.5%. This for the mean during some divided parent and child voices have strong spatial locality. So local search can handle most organization point queries. On average, our method is 2.14 times faster than the baseline. The median time is reduced by 69.4%. The mean level of PVH access is reduced by 97.3%. These numbers show that the method reduces the mean query cost. Fewer PVH accesses also lead to real-time reduction. The plots show an important trend. Large and more expensive cases benefit more, with deep subdivision. Rapid queries grows quickly. In that case, spatial locality becomes more useful. So the method is valuable for complex matches and state accuracy requirements. Spin is used only when the result is still correct. This slide compares the low and top boundary from our method with the baseline. The points are very close to the population remote line. This means the two methods give almost the same bound values. The maximum difference is very small. So the acceleration don't change the final result. This is consistent with the algorithm design. When the local bound is enough, we run safely. When it is not enough, we run the global image query. The final low and upper bounds stay consistent with the cascading upper bounds baseline. So the message is simple. We get the speed up by reducing repeated queries by making the accuracy requirement. We also test harder city high density overlapping match pairs. In this experiment, we use 400 dimensional match pairs. They have overlapping geometry, but their topology can be different. This is more challenging than a simple simplified match comparison. As a result, it is better. The average speed up increases to 2.55 times. Image access dropped by 170.6 times. Also, 78.9 model repeats have a image at least 99.5%. This helps us that deeper subdivision can make spatial locality stronger. Child voices become close to their parents. The inherited DNA surface becomes a better initial guess. So this result confirms the mean trend. The method becomes more useful when the baseline computation becomes more expensive. We also test several stress cases and limitations. For the large model, the method gives 12.29 times speed up. This shows that the method can be very effective when the query cost is high. For the some feature case, the method still keeps incentives and gives faster computation. However, the method is not always faster. There are two main limitations. First, for very simple matches, the subdivision is shallow. Also, the latency overhead may be larger than the benefit. Second, the method depends on topology. If the match has missing topology, no way for the structure or transform data, or the value neighborhood may not be reliable. So the method fallback to the global image query is more open. So our method is a space-for time trade-off. It works best for complex matches, deep subdivision, and straight accuracy settings. Let me summarize the main points. How to instance the computation is manipulation point queries. in the baseline and tell the overseas that globe previous queries. Our method use visual catches to reduce these repeated queries. The method has three key parts. First, carry goes visual initialization. We use the parents in the surface. Second, when we make a whole search gives a local outbound. Third, double brownies gives global search with the local result and enough and rate needed. Across more than 1,380 test cases, the average speed up is about 2.27 times. The heaviest is about 99.5% more than 70% of the data. The accuracy is still consistent with the baseline. For future work, we want to an adaptive map as for suitable matches. We also want an adaptive search range based on local service culture. That's all. Thank you for listening.
Thank you for the nice work. Any questions from the audience? For you, okay. Because I understand you recently published a paper and talk about GPU-based cost of this. You have some great questions. Expect.
Right. Thanks. Yeah. So I understand all of this. We are the most issues. Also, I mean, okay. Another question. So, according to staging units, hash ratio, hash hitting ratio wasn't that high, but was it 30% of data? But how does that translate to explanation ratio actually kind of price? Sorry, I mean, for your central management, can we discuss in the association? My second question, is it possible to call the management to GPU? No, I don't have exactly. But it's possible. I have read to some people about use GPU to accelerate the hardware business function. In the future, it may the GPU may be using in this set. Yeah, I think in principle it's should basically we use some for the parents and child. So I think it's in principle it should it's possible to combine with these two works. This
Thank you. So just a follow-up, which looks like your mixer is like a jet by speed up. So the can be applied on the CPU or the GPU. That might have any correct.
This program is only usually CPU. Yeah.
And what's the baseline? You talk about its 2.27 speed up. So what's the baseline method or implementation you are doing with? I mean, what's the baseline compared method for this speed up? Because you can go and run implementation altogether. This one is based on which method of implementation for this speed up? We can discuss on that. Thank you. Any other questions? Okay, if not, this next speaker team. The fourth speaker, the author is here. So the first paper is knit to vector, 3D knitted texture reconstruction from unconstrained images while differentiable vectorization. The presenter is Yizhou from Shandong University from China.
Thank you for your introduction. Good afternoon, everyone. I think. Sorry.
did it jointly together with colleagues from over on using generative AI to multiply the arithmetic cat. Specifically here, we dealt with designing and modeling of voltage connections of frequency straight from a natural language input. Or the data we use to publish online model. So for everyone to use the data to do some further work on it. So what was the motivation? Basically, I don't know how many of you have a mechanical engineering background and during the first semesters. You're dealing with doing first technical drawing by hands. You have an idea of part in mind, the time you have to take, the time it takes until this idea is actually here paper in front of you. It's quite a long process. Then of course 3D CAD modeling somehow ease this process a little bit, but still you need to know, or you have to, we just certain type of training to actually be efficient, and still quite a long time to go. So I grew up with Iron Man films and comics. Of course, it's the easiest way if you have some smart system next to you, just talking about the constraints and how you punch like it's going to be generated then more or less directly. So this is the core idea. Want to go from words to geometry. Where is this word precision? So in Ryanberg, earlier approaches focused either on downstream code generation or isolated parameter extraction. One handle of the full pipeline, actually having interactive parameter collection through to the finish and design model. So we were one of the first systematic persons integrated versus modular large language models in this field evaluation and so on the task it was from an engineering point of view it's not a single task, it's the design of multi-connection. So we wanted to have automatic generated code with thread and that which is of course counterpart to a code. Therefore, we need to collect a total of 5 parameters. The load time, where we have the static or dynamic force, which we choose to be more or less flexible or random between 10 Newton and 1 meganewton. Create for the bolt, basically referring to a bolt's strength and engineering standard of how the connection is actually calculated and the length of the bolt connection. We're going to expand for the system to first deliver a correct friction diameter, basically derived from the attention standard, and second to use the executable recappa, which becomes or which then is part automatically in the environment. We tried to talk for different logics. We have one all meaning we used one LLM, which did all tasks one, so a dialogue, extraction, sizing, and code. The second one splits the language from the species, so we have a chatbot model, and a second model which does the signing, so a calculation of us. In the next step, we're again a bit more granular, also isolated the numeric reasonings. Now at this stage, we have a total of 3 elements used, one for the chat and parameter collection only, the second one only for the calculation, and then the third one only for the code generation. In more detail, for all-in-one, we have a single fine-tuned GPT-2, which handles the dialogues, extracts all parameters, computes the diameter, and writes one. All in one network combined. So it's obviously also the simplest pipeline you can imagine, and also the fastest to train, since it's just one you have to train. But it's also asking quite a lot of balance and objectives there are very heterogeneous. The second one decouples exactly those objectives. We have still achieved two model, which is the chat model, parses the dialog and outputs when a structured parameter list to the design model. For the design model, we use the separated object model that turns that list into the FreeCAD model. So here we have split the language into pieces. First, we reduce the conflicting learning signals for the model, and most of the model capacity can go actually into the engineering computation. In the third model, we took the final step and isolated programs with numerical reasoning into a dedicated calculator with the code generator now with the code only. Yeah, each model is now exactly one narrowly defined function, and we will see later on the results that it's exactly the properties which were modeled later on the accuracy. A few words on the dataset and training. Since of course reproducibility matters a lot, we had about 2,000 samples which we generated per pipeline, and yeah, of course, they're all synthetic. Generated then dialogues about theme, right phrasing to avoid overfitting, and so obtain parameter diameter pairs, which were computed analytically and inserted in this dialog list. For models, we used the GPT small with 124 billion total. Media version and also a code share a 350 billion remote version for the code. Fine tuning, we used LoRa and PAF, so that everything we did for drop within one media A40. It was especially important for us to use small models and to work locally because it's also relevant for engineering access, quite relevant. Also, smaller enterprises could use the approach, and we do not need to give only engineering knowledge over cloud to the computer models, so that you can exactly stay sure that everything we have is also locally. So we did choose the small models by purpose. So now I'm already coming to the slides, the results. We have split it up in different matrices, starting with the dialog family, which worked perfectly well with free modeling approaches. Nevertheless, for parameter extraction, for all in one model, had a 0% error. The other two have a small error right here. Most important thing is the design size of the error. Here we have 53% error on the and then the more granular or more decomposed we are, the better it is. We have a 2% error for the second model, and we have a 0% size error for the finest model, which means that the modularity lies actually accuracy. The costs, of course, when we have a certain longer pipeline, if you have a look at the evaluation costs, quite stable or across 3 months. This is fine. For the training time, we see that we have a long training time. For all in one was, as already said, very efficient. And the CCC model was also quite reasonable with 63 minutes training time here. And we also see more, with increased numbers of LLMs used. The better it was defined task, we have specialized LLMs for each one. This is also reflected in the total slicing error in the end. So one question is, of course, why did it fail at sizing? And this error is due to how we defined the first range. We said we wanted to go from 10 to 1 megameter, and we used the cells to be
more or less evenly distributed across this land this range. But now everything which is close to payment is obviously in the further section. So based on the not give certain weight to the norms, we ended up having a very high population and training data for them further. Nevertheless, we see that regardless of the popular calculator did not fail at this job. So of course you can also say if data set or balance, maybe also the whole version would be more efficient. But as my from engineering practice, it's the case that the company has one program, one configuration which dominates the remaining. So if you went into actual work with data, you will obviously always have some balance in the data, and perfect balance data is always something which is just existing in theory or theoretical work only. So I also want to show you some qualitative results. We have here taken pipeline as it does produce three categories. So here, for instance, it's all with Australian. See that basically here we give the full parameters once. It starts modeling right now. For the second one, we have a little bit of a longer dialogue. Let's see when the system captures object dialogues when ended as soon as the parameter list is completed. And I took three very different old connections so that everyone can see that we actually use different standards for calculation. The important thing is that this leads me to the limitations of study scope use. It is a fixed parameter scheme. So the system assumes a fully populated set and does not work with missing parameters. So it does not do any reasoning about which parameters task B. Only works if we actually have all 5 parameters provided. We currently use only a static node. So it's a class, it's a basic approximation. We don't need any fatigue, we don't have high temperature, we don't have non-standard geometries, and so on. So that in the end we have a very simplified case, but this is a benchmark, also give us a chance to evaluate it quite efficiently, and so that we can ensure the credibility of the framework. And it's a benchmark which you can substitute to other tasks and not general purpose design substitute state. So it was concepts and demonstrates that general value the deterministic capital flow can work under controlled conditions. Which lead me to the following conclusions. We have contact fine-tuned LLMs. They can do accurate reproducible design information even with only around 2000 samples. Modular separation turns a reproducible 53% sizing error into an error-free sizing and a relatively short training time and small models as GPT-2 small and CodeGen 354. They are both sufficient when each task is narrowed down. Crucially, we can make the approach extensible. We can swap the schema we have here to other parts. For instance, we can address the same pipelines for flatulence, gases, and other final parameter design tasks. Actually, part of our future work is to combine this together to first do 2 or 3 flashes. Let's say, okay, I want to combine this certain number of flashes with a number of screws. Then we can also increase the engineering complexity by then have a multi-screw connection and task to have, for instance, both connections, but also where are holes should be arranged. So that's it. Thank you for your attention. I'm happy to take questions.
you can access the paper and also become higher documents. Thank you very much.
We have time for big questions.
So thank you for the presentation. Until now, you just talk about the standard component like anyway. How do you think it can be extendable to any shape? I mean, when you have, because here you have just known parameter that you have to fit, but some most general case, you have parametric design and you don't know exactly where is the parameter, or you have different combination of parameter that can the same path. I mean, how do you see the future or extend your work in that case?
Yes, so we thought a lot of this, and currently you can say that also from the other works, the data used is mostly up to 5, 6 different configurations. Also here for the screw we have one category that we have to make 1, 2 sketches for the screw head and for the shaft. Then another operation is to edit the thread, and yeah, basically a third one, but not in the end. It was just a sketch and then extruded. So within this number, so 5, 6 cat operation, it's quite efficient, quite error-free, so error-free in a certain sense. Because dimensioning is another issue. Parts are not well standardized. Anyways, if you increase the number of cat operation, that's not working very well yet. But this is probably due to the fact that usable data set with up to 50 configurations is not available yet in a certain size and actually do the thing. So we're working on a data set for doing actually more generalized works. And we're also thinking a lot about how we could use technical drawings. Because from a technical drawing, you have basically everything you need to make a real product. So if you can have the same structure but implement different JSON point once when it should be also good enough for this method to reduce parts correctly. It's also important when you don't want to have meshed geometry, you don't want to have something triangulated, you want to have a parametric category. So, and if you were doing, I don't know, even if the two of us are designing a quality in FreeCAD, we will do it a little bit differently. We will do the sketch a little bit differently, we will select the rotation axis a little bit differently, and so the CAD sequence for the design tree inside of the program will look different, but leads to the same result. And this is gonna be interesting or hard to evaluate yet if a model does the right thing, because we're analyzing the CAD sequence, we can look completely different, but the result can be exactly the same.
Any other question?
Thank you. I was thinking about you can design in part by using the LLM or other stuff. Is that possible to consider the manufacturable design? I know that if you create anything, you need to produce it as well. So you need to consider some manufacturing operation, and it must be cheap as well. So what can you do on that side also?
The manufacturability side of parts. Yeah, actually, this is to start. This is the reason why we want to have parametric parts, because you need a parametric CAD model for most manufacturing existing processes for most CAD models. You want to, so in optimization, you often have manufacturability constraints or something like this.
You can use it or think about adding some kind of knowledge category. So yeah, for instance, if you do it by hand, a designer for machine parts have a content level, a cat level by his sides with what shapes to do, what shapes not to do. We can have this as a training data, or you can just hard code and put it into the task description for the LLM that it should only use with event shapes. Actually, when we are going to more complex parts, we are want to do the same thing. We want to hard code the first step, when we say we only want to use this 12 different primitives, and everything should be a combination of these 12 primitives in order to keep the parameters controllable. And for manufacturability, you could think about similar things. So if you are for casting, that you always have to consider the size for the forming, or that you have form of two halves, so that you have must separate it, undercuts, things like this. So I think it's quite, if you can, it's quite straightforward. You have as a catalog or as PDF files, you can pass them alongside if you want and search or sort all of manufacturing.
Any more questions? Maybe I actually have quite a few questions, but due to the lack of time, I think we'll discuss later on. So let us thank Tobias once again for the wonderful talk. So we now have the next talk, topology enhanced DPSDF with applications. The authors are Dong and Lee. So the talk will be presented by Lee. I think we have an interesting one on SDF in the morning by Matthew Devon, who presented SDF. So there is a deep SDF coming now.
And thank you for your introduction. And good afternoon, everyone. Today I will present our work topology enhanced device staff with applications. And I'm Dong Lian, and my corresponding author is Ling Hongli. We are from School of Mathematical Science, Zhejiang University in China. And this presentation has four parts. First, I will introduce the background and preliminary of SDF-based shape learning and persistent model. And implicit neural representation represents three-dimensional shapes as continuous implicit fields, and in particular, some data functions widely used because they provide a clear geometric interpretation. The surface is defined at the zero level size of the scale field. And shape-based learning stands representative representation from a single shape to family shapes, as shown in the lower left. The DeepSDF autodecoder framework uses a shared decoder with shape-specific Latin codes, and the decoder takes a special coordinate and a Latin code as input and predicts the size function value as an access location. Most existing autodecoder-based methods mainly rely on geometric constraints to improve size function learning. However, these constraints cannot explicit guaranteeing global topological correctness. And as shown right, geometry-driven reconstruction may still produce disconnected parts or broken structures. This motivates explicit topological supervision for implicit shift-based learning. And we first introduce the cubical complex and filtration in our method. And a cubical complex is built from vertices, edges, squares, and cubes, and is shown in the figure lower left. And the left figure shows the elementary cubical cells, and the right figure shows how they are sum-point for a cubical complex. And importantly, a cubical complex is closed on the Artesian faces. This means that if a cube is included and its faces, edges, and vertices are also included, and the growing sequence of subcomplexes controlled by the threshold T, and as T increases, more cells enter the complex. And for a sun distance field simple on regular ground, the ground cells naturally defines the cubical complex, and we assign each cell a value from the sun distance field using the maximum value over its vertices. And then as the threshold T, KT contain all cells whose assigned value are no larger than T. And predictive homology records it when the topological feature appears and disappears along the filtration. And a persistent diagram represents these events as birth dice points. Each point is written as B and D, where B is the birth time and D is the dice time of the topological feature. And for some distance function-induced filtration, and this means the feature appears at the threshold B, disappears at threshold D, and exists between these two thresholds. And the figure shows a simple two-dimensional example of persistent homology. And on the left, we have a scalar view depending on the two-dimensional domain, and different colors indicate different scalar values. And in the middle, the filtration and barcode show how topological feature evolve as the threshold increases. Connected components and loop structure are born and later disappear during this process. And on the right is present time and death events are summarized together, points in the persistence diagrams. And each point corresponding to one topological features. And next, I will explain how these points can be mapped back to the sign distance field, and so that the topological rules can be used for gradient-based optimization. And through the topological inverse mapping, each persistent point is associated with two critical cells, and the birth cells and the death cells. The birth value and death value are the scalar field value of these two cells. And in filtration, each subcomplex is obtained by adding cells according to their scalar value. When the threshold reaches a critical value, a new critical cell enters the filtration, and they may create it or destroy the topological feature. And in this figure, the critical cells are drawn as points on the one-dimensional scalar function. And under Mellon conditions, such as local fixed persistent Perry laws defend on persistence diagram points is differentiable almost everywhere. And by the chain rule, its gradient can be propagated from the persistent point to the critical scalar value, and then to the some distant field. And this provides a basis for using persistence diagram-based tools in topology-aware optimization. And next, I will present the topology-aware optimization framework. And this is an overview of the whole framework. And we first pre-train an autodecoder to learn an implicit shape space. And at test time, the decoder is fixed, and we only and the only license code is optimized. And starting from a geometry-only reconstruction, we simply predicted sign distance field on regular ground on a regular grid and compute its persistence per diagram. And this diagram gives us explicit topological information about the decoded shape. And we then construct the target persistence diagram. For reconstruction, the target comes from a ground truth shape. For editing, the target is obtained by modifying selected persistence points. And finally, a region-based topology will use AGI to refine the lighting code. And in this way, the decoded sign distance field is adjusted within the third shape space in both topology repair and topology guide edit. And first, we introduce the topology feature region, and a persistent point B and D represents a topological feature that appears as threshold B and disappears as threshold D, and therefore these features exist from B to D. And the left figure shows the shape and its persistent diagram, and where selected points corresponding to topological structure of the shape, and the right figure shows different T-level size. As T changes, the level size topology also changes. And for each threshold T, the gray region in the persistence diagram indicates which feature are aligned as the threshold. And since the surface is the zero level size, and we focus on T equals 0, and thus a persistence point is related to the surface topology. If B is less than 0 and D is greater than 0, and we define the topological feature region as a region containing persistent points whose features are aligned at the zero threshold. And then we construct our region-based topology aware laws. And first, we construct the target persistent diagram from the ground truth sign distance field. And specifically, we selected the ground truth persistence point inside the topological feature region. And for each homology dimension K, and these selected points represent the desired topology near the zero level size. And for the predicted sign distance field, we also compute its persistence diagram. And since the predicted topology feature may not lie exactly inside the straight feature region, and we select candidate persistence diagram points from a relaxed region or ipsium. And then we match the target point to the predicted candidates. This is formulated as an injective assessment based on the square two matching cost, and the matching loss minimizes the square distance between each target point and its matched predicted point. And in this way, the matched loss established correspondence between the desired topology and current predicted topology features. And after matching or matched predicted points inside the feature region are regarded as undesired topology. And the pinch push them out of the region will match the points outside the straight region are pulled back into it. And the partition line LT controls the exclusion direction. It determines whether the point is encouraged to live through the boundary B equals 0 or D equals 0. And the topology regularization term penetrates the persistence lines of predicted features and helping to surprise insignificant topological noise. And together with the methods, this term form of full region-based topology will lose. And then we summarize the final optimization objective and the topology enhance deepest framework. And at the top, the final objective combines two parts, topologic values and the geometric those. And the topologic values including three terms, matching rules, penitent rules, and the regular flashing rules, and sum over different topologic dimensions. And the geometric rules includes field rules which measure the difference between the predicted sun distance function value and the ground truth sun distance function value, and the economic rules which encourage the predicted field to satisfy the unit gradient property of sun distance functions. And here you see how x denotes the sun distance field values predicted by the decoder as point x, and will view ground truth of x denotes the corresponding ground truth sun distance function value. And the lower part shows the overall framework, and the input spatial coordinate is first processed by position encoding and then combined with a learnable Latin code, and the fixed pre-trained decoder predicts the sun distance function value. And during reconstruction, we first optimize the Latin code with the geometric rules to obtain a false shape. Then we add the topological values for further optimization. And on the right, the predicted persistence diagram is compared with the target persistence theory. And the mentioned pinch and penalty and the regularization terms as a PD points and update the Latin code. And next, I will show experimental results, including quantitative and qualitative comparisons. And we first show the quantitative results for topology enhanced reconstruction. And we evaluate the method on ShapeNet V2, including checks on sofa and table. And for one-dimensional topology repair, and we use 265 selected chair model who has reached one-dimensional topologic structures. And the baseline including DPSDF, IGR, and DIGS. And DIGS is modified for stable training, and we report both geometric and topologic metrics, including transform distance, post-off distance, and field level L1 area, and the topological metrics including average between numbers, differences, and success rates, and where success means that the predicted between number match the target topology. And as real table our method consistently preserve the correct connectivity across all four categories, and compared with the baseline, it reduces topological errors while keeping competitive geometric accuracy. And for one-dimensional topology, recovery on shares our method also shows a better loop preservation. And this is qualitative reconstruction results. And the column corresponding to chair, lamp, sofa, and table. And the first row shows ground truth, and following rows compares four methods. And the baseline method can recover the rough objects shape, but they often produce broken parts, disconnected structures, or encrypted connections. And our method preserves the global structure more consistently, and it produces more connected shape and better maintaining important topological structure across different categories. And this is a qualitative results of zero-dimensional topology repair. And therefore, dimensional topology describes the connected components. And in each example, the left plot shows initial reconstruction, and the right plot shows the results after topology-aware optimization. And in the persistence diagram, red points are predicted zero-dimensional persistence points. Before optimization, several right points lie inside the topological feature region, which indicates extra connected components or disconnected fragments in the shapes. And after optimization, these only-zero points are pushed more out of the feature regions. And this is a quantitative results for one-dimensional component repair. And in the persistence diagram, red points are predicted one-dimensional persistence points, and blue points are the target points. And the green line shows the matching between the target points and predicted points. And after topology well optimization, they match the predicted points fall back into the feature region. And as a result, the desired one-dimensional features become active again, and the structure repair in the reconstructed shape. And this is a loss curve during topology repair optimization. And the left plots reports the total loss, and the right plots reports topology loss for four shape line categories. And the x-axis represents the optimization later reaching, and y-axis represents the mean loss value. And then we show the results of one-dimensional topology editing by removing loop features. And different from the topology repair, here the goal is to remove selected loop structures. And we start from the chair walls whose one-dimensional topology has already been successfully repaired. And for each model, we compute the origin one-dimensional persistence diagram. Then we select zero persistence one-dimensional points inside the topological feature region and remove them from the diagram. And the remaining points are used as the editing target persistence diagram. And next, we'll optimize the Latin code toward this edited target persistence point. And in this experiment, we use a large slope parameter T, so the selected points are dragged below D equals 0. And for one-dimensional topology, this means that the corresponding loop features are removed by filling holes. And the table gives the quantitative editing success rate under different settings, and including remove one, two, or all selected one-dimensional features. And the lower figure shows qualitative examples for removing one-dimensional features. And after optimization, the selected loop features disappear and in the reconstruction shape. And the top row shows a setting for removing two one-dimensional features. And the bottom shows the setting for removing all selected one-dimensional features. And selected predicted points are drawn below d equals 0. So the corresponding loop features are removing by finite close. And really you can see that shared by close omniscient loops or other loop-like structure are filled and removed while the main shape is still maintained. And next is two-dimensional topology. And here, two-dimensional topology corresponding to void-like structures. And the target prediction diagram is constructed by selecting one two-dimensional homology point inside the topological feature region. And this point represents the desired internal cavity. And in the persistence diagram, the blueprint is the target H2 feature. And during optimization, the matched predict point is pulled into the target point and into the topological feature region. And as a result, the corresponding cavity feature become active as their level size. And geometrically, the table shape develops an internal cavity, and on the right, we simple point cloud from the editing shape and user transparent visualization, so the internal cavity can be observed more clear. And then we can compare the continuity-based topological rules with our topology variables for their.
Can you just conclude a minute?
Uh,
Can you just conclude? We're just overshot the time, quite a few minutes.
and we also define that still shape space learning explicit topology approximation and rebase persistent topology rules enables target-driven topology control in latent space and measuring for the structural consistency and supports topology repair and topology edge. Thank you.
So it was quite an interesting talk, but due to lack of time, we can take the questions offline. Thank you. Thanks, speaker, once again. Now, call upon the last speaker of this day one, the Spm Smi conference. The title is a data-driven anisotropic refinement strategy for an LRB spline surface approximation of 3D scattered particles. This will be presented by Alberto. Correct? Is that right? Hopefully, is that right?
Which I have done into operation with my supervisor and Generato and with the Kirlano. So,
Yeah, sorry. My talk will be in my talk we discuss about my new method to refine the LR spline basis function in order to prospect parameterized scattered point cloud using G-spline surfaces. In my to let's say refine the spline surface, we use a neural network to detect the feature of the scattered point cloud, which will be used then in a refinement process to refine the corresponding error mesh, which will be used in the final step to fit the final spline surface. So, first of all, I want to describe to you the neural network that we introduced, which is essentially a shared multi-layer perceptron, which is applied independently on each point of the point cloud, and it is composed of different independent layers, which are then concatenated after some iteration after some level of the network, and the input for this neural network is extracted from the independently from each point of the cloud by analyzed by the same structure features from the neighborhood of different sides of each point. In this case, we have four different neighborhoods of dimension 16, 32, 64, and 128, which are then concatenated to obtain at the end the probability U of a point of being sampled from a feature of the original model. So, to train our network, we have used the fit for CAD dataset, which is a dataset which is composed of annotated point cloud, which are of course annotated with the underlying geometric primitive from the which the each point was extracted. And the feature points are extracted as obtained from the intersection of the geometric primitive. So in this case, we define the feature points at the boundary of the geometric primitives. Then here we can see some results of the neural network. And on the left, you see the original scattered point cloud, and on the right, you see the result on the parametric domain of with the parameterization which we have already have as input. Then I will briefly introduce LR splines, which stand for locally defined basis spline function. And I choose this basis function because they allow us to introduce an isotropic refinement inside the computation of the parametric LR mesh, as you can see from the left mesh, which has only anisotropic refinements. And the exact strategy we use is called HOS2, which stands for non-nested support structured refinement strategy. And we use, and you can see on the bottom an example of application with also an isotropic refinement, because the HOS2 refinement also allows for an isotropic refinement. And this strategy combines the structured fat refinement approach, which gives the node which has the length of each node on a basis function, and with a mesh line extension step, if required, when the mesh line extension is performed when overloading is detected inside the computational mesh. So we can see here oops, that we want to refine the string basis function, which the support is highlighted the string color. The color indicates the direction where we want to refine the basis function. And we can see that first we do a structural refinement, halving the node extension in each desired direction. And then we perform the mesh line extension by extending the mesh line where this overloading of the basis function is present. And thus we obtain an alignment LR mesh with no more overlapping. So then a crucial part of our approach is the feature driven refinement, which is composed of two different, let's say, steps. The first step consists in assigning to each detected feature point a direction which is based on its neighborhood of feature points, and can be one of three different directions: vertical, horizontal, or diatic. And then each basis function which has support over at least one feature point is refined in the direction determined by majority vote of the point inside the support of the function. Here we can see some example of the mesh, the results we have reported also before. Sorry for the quality of the local picture, but that was better. You can clearly see that it follows the feature detected by our neural network. Then the last step consists in a fitting of the surface, which is made to approximate the original scattered cloud. And to do this, we simply use a standard penalized square approach. But the key point of our approach is the fact that this reconstruction happens only once per, let's say, in all the execution. While in other approach like the standard error-based fitting approach, this reconstruction is performed at each step. Thus, our approach is able to drastically reduce the computational cost of the fitting process. Here we have some other examples of this fitting step. Here we have a brief flow of our procedure. We can see that we first perform the NFT step, which consists in let's say, applying our neural network. Then there is the neural feature detection based marking, which is the step where we mark the basis function, and also we assign the direction for the refinement. Then there is the refinement itself, which is performed for a certain amount of iteration, which is chosen by the user. And then only at the end of the procedure, we solve the penalized square problem, thus take the reconstruction with the surface. And we also noticed that our network is also pretty robust noisy point cloud. In fact, we can see that the results with noisy point cloud are pretty consistent with the one with noiseless point cloud. The only thing we are using is the anisotropic refinement inside the mesh, which insert a little bit more of degrees of freedom inside the mesh. But otherwise, the results are pretty similar, as we can see here when we compare refinement without and with noise, in which we can see that the results are pretty similar.
And to sum everything up, we have that our, as I said before, our approach is way more efficient than a traditional error-based approach where the surface is reconstructed at each iteration of the procedure of a model, but to do a error-based refinement, it is also needed to compute the errors of the reconstruction at each step of the iteration. While in our approach, we don't need to compute the error of the reconstruction at any point. And we have also observed comparable accuracy to error-based model. So we are gaining in computational cost while retaining similar accuracy. Also, we have also seen very good robust race noise in our approach compared to other already existing approaches. And we have also developed an approach which is able to reduce the number of the real freedom inserted in our solution.
Thank you.
We have quite a few minutes to ask few questions. Going from the top, yeah.
Thank you very much for this very nice talk. I want to ask why you use MR spice instead of THP spice.
Yeah, I use LR spline because they allow to insert an isotropic refinement inside the mesh, while the traditional THP splines doesn't allow to introduce an isotropic refinement.
And then some work like PyTorch, they allow this anisotropic refinement. Did you have a look at that?
I didn't have a look to this particular paper. I will of course look into this paper, but let's say for many years, spine were the let's say solution for isotropic refinement.
Okay, thank you very much.
Welcome.
Any other questions? Okay, maybe I just ask one question. So all the surfaces are open surfaces, like what are the results that you showed? Suppose if the surface is closed, for example, for a bottle like this, if the surface is closed, have you got some results for that? Because the mapping may not be one-to-one the parametric space.
No, these are not closed.
Yeah, so did you try any closed?
No, I never tried closed surfaces. I always one she's not only non-closed surfaces. So I never wanted
the idea how to handle them.
Let's say one analyst work perfectly with closed, let's say, surfaces. The problem is with the parameterization.
Yes.
You need to find an adequate parameterization, which is not so easy. And probably you will need to work more with volumes than in this case.
Any further questions?
I could see a face model, which is a symmetric and 3D model, but its parameterization is not symmetric. So why is it?
You mean this one?
Maybe page 10. I don't know. Yeah, this one.
Yeah, let's say parameterization doesn't need to be symmetric. Let's say there are various ways for the parameterization. These are obtained with the inversely stance method, and it doesn't guarantee to obtain a symmetry inside the parametric plane, even if the original point cloud is symmetric.
It's not a reasonable expectation to have symmetric parameterization here.
Not really, because first of all, I'm not even sure if the point cloud is
really symmetric, probably it is, but I'm not really sure. Secondly, maybe there are some factorization method which retains a symmetry of the parametric domain, but not the one we are used, and I don't think this is a real issue in our case.
So, no further questions, so let's thank the speakers. So this concludes our first day session, and once more, let us thank all the speakers of this session. So we'll be here by 9 a.m. tomorrow. Yeah, so please be here by 9 a.m. tomorrow.
Very